18,000 miles per second past the edge of our solar system, deep in the constellation Scutum. A single star is doing something the laws of physics say is impossible. Its surface stretches past where Saturn would orbit. Its volume could swallow 10 billion of our suns. And according to every textbook ever written, a star this size should not be able to exist. You will see why physicists are arguing about it, why one measurement could rewrite stellar evolution, and why this giant might already be dead. If cosmic mysteries pull you in, hit subscribe before we go further. This one gets stranger fast. Prepare yourselves. We begin. Look up on a clear summer night in the northern hemisphere. Somewhere between the brighter constellations of Aquila and Sagittarius sits a tiny, almost forgotten patch of sky called Scutum. The name means the shield in Latin. It was carved out of the heavens in the 1680s by a Polish astronomer who wanted to honor a king who had just won a battle against an invading army. Scutum is small. It is faint. It contains no star brighter than third magnitude, which means almost nobody notices it. If you point at it without a chart, the average person will think you are pointing at empty sky. But that emptiness is a lie. Behind that quiet shield lies one of the most violent neighborhoods in our entire galaxy. The Scutum Centaurus spiral arm cuts straight through this region, packed with dense clouds of gas, newborn stars, and dying giants. Hidden inside it sits a graveyard of monsters. Scientists call it a red supergiant cluster, and Scutum holds more of them than almost any other patch of sky we know. One of those monsters is the reason you are watching this video. It is invisible to the human eye. Even with a decent backyard telescope, you would never spot it. The dust lanes of our galaxy block the light. You have to look in infrared, which is a kind of light our eyes cannot see, to even find the thing. And when astronomers finally pointed the right instruments in the right direction, they saw something that made them quietly panic. A single red point of light, glowing with the energy of nearly 500,000 suns, sitting at a distance so uncertain that even today nobody fully agrees on it. A star so swollen that its outer layers, if you placed it where our sun is, would reach beyond the orbit of the ringed planet you can sometimes see in the evening sky. This is the constellation that hides our largest known star. It is also the constellation that hides our biggest astronomical headache. Because here is the strange part. Scutum should not, statistically speaking, be hiding giants like this. Red supergiants are rare. They burn through their fuel so fast that they only stay in this phase for a few 100,000 years. That is a blink of an eye in cosmic time. To find dozens of them clumped together in one tiny constellation is like walking through a forest and finding all the oldest trees standing in a single circle. Something happened in this part of our galaxy. A wave of star formation, maybe 20 million years ago, lit up thousands of massive stars all at once. Most of them have already died. The ones that remain are running on borrowed time. Every one of them is in the final act of its life. Every one of them is going to explode. And one of them, the largest of the bunch, the one whose name you will hear over and over again in this video, sits right there in the dust, slowly tearing itself apart from the inside. The shield is hiding a corpse that is still walking. To understand how a single point of infrared light could throw modern physics into an argument, you have to start with the man who saw it first. His name was Charles Stephenson, and in 1990, he found something he was not looking for. Charles Bruce Stephenson was not chasing the largest star in the universe. He was just doing his job. In the late 1980s, Stephenson worked at the Warner and Swayze Observatory in Ohio. His specialty was patient, careful, almost boring work. He would sweep the sky in infrared light, looking for cool red stars that the human eye misses entirely. Most of what he found was unremarkable. A red dwarf here, a distant giant there, pages of catalogue entries that almost nobody would ever read. Then, in 1990, he aimed his telescope at a stretch of the Milky Way deep inside the Scutum constellation. He was using a technique called objective prism spectroscopy. which means his telescope spread starlight into rainbows so he could identify what kind of stars he was looking at. The plates came back, he developed them, he started cataloguing, and he saw something odd. In one tiny patch of sky, his plates lit up with a cluster of red signatures. Not one star, not two, many, all glowing in the same deep red wavelengths that mark a very specific kind of dying giant. He had stumbled onto what would later be recognized as one of the richest red supergiant clusters in the entire Milky Way galaxy. He gave the cluster a simple name, Stephenson 2. He then numbered the brightest stars inside it. The brightest of all of them, the most luminous point of red light in his entire field of view, he labeled with the number 1. That brightest star was the monster we are talking about today. But here is the part nobody talks about. Stephenson got the distance wrong, wildly wrong. When he looked at how dim these stars appeared and assumed they were all red supergiants like he expected, he calculated that the cluster had to be sitting about 30 kiloparsecs away. In American units, that is almost 100,000 light-years. That distance would have placed Stephenson 2 on the far side of our galaxy, beyond the central bulge, almost outside the Milky Way entirely. That number was completely off. Later studies, using better tools and more careful measurements, brought the cluster much closer. Today, astronomers estimate it sits around 18 to 19,000 light-years away. Still far, still deep inside our galaxy, but less than 1/5 of what Stephenson originally thought. Why does this matter? Because every other property of the star, its brightness, its size, its temperature, depends on knowing exactly how far away it is. Move the star closer, and it shrinks. Move it farther, and it grows. The whole controversy surrounding this monster star traces back to one frustrating fact. We have been measuring it wrong since the day it was discovered. Stephenson published his catalogue quietly. There was no press release, no magazine cover, just a list of stars that other astronomers would mine for decades. For 17 years, almost nobody touched it. The cluster sat on bookshelves and in database entries, waiting. Then, in 2007, a team finally took a serious look. They confirmed the cluster was real. They confirmed it was packed with red supergiants. And they renumbered Stephenson's brightest star. In their catalogue, the brightest star got a new label, number 18. That tiny renaming, from 1 to 18, would eventually echo across science articles, documentaries, and television specials around the world. Because what came next was a measurement that broke every model. A measurement that, if correct, meant we had been wrong about how big a star can possibly get. Step back from the single star for a moment and look at the neighborhood it lives in, because the neighborhood matters. When astronomers finally focused on Stephenson 2 inches 2007, they expected to find a handful of red supergiants. What they found instead was a stellar massacre waiting to happen. Inside that one open cluster, packed into a region only a few light-years across, sat at least 26 confirmed red supergiants. That is the largest known concentration of red supergiants anywhere in our galaxy. To understand why this is shocking, you need to know how rare these stars are. A red supergiant is the end stage of a very massive star, something at least 10 times heavier than our Sunday. These stars burn so hot and so fast that they only last a few million years total. The red supergiant phase itself is even shorter, a few 100,000 years maximum. After that, the star explodes. Most galaxies have only a few dozen red supergiants scattered across their entire structure. Our Milky Way contains hundreds of billions of stars, and yet only around 200 red supergiants have been catalogued in the whole thing. To find 26 of them sitting in one small cluster is like walking into a single classroom and finding 26 lottery winners. So, how did this happen? The answer is starburst. Roughly 14 to 20 million years ago, this region of the Scutum Centaurus arm went through an enormous baby boom. A massive cloud of cold hydrogen gas collapsed and ignited, lighting up thousands of stars at almost the same moment. Most of those stars were too small to interest anyone, but scattered through the population were a few dozen monsters, stars massive enough to live fast and die young. Those monsters all aged together. They all entered their red supergiant phase around the same time. And right now, in the cosmic blink we happen to be living through, they are all simultaneously preparing to explode. Think about that for a second. Inside Stephenson 2 sits a row of countdown clocks, all ticking towards zero, all set to detonate within a window of cosmic time so narrow that we get to watch the whole show in slow motion. When astronomers map the cluster, the picture gets stranger. The supergiants are not all clumped at the center. They sprawl. Some hug the core. Others sit at the edges, almost detached from the main group. A few hover in the surrounding region in a smaller subgroup that researchers call Stephenson 2SW, located to the southwest of the main cluster. And one star, the brightest of them all, sits in a position that does not quite fit. It is slightly offset from the cluster center. Its measured speed through space is different from the others. Its brightness is so far beyond every other supergiant in the group that it should not statistically be there. For decades, scientists have argued whether this star belongs to the cluster at all, or whether it is a foreground object that just happens to lie along the same line of sight. The argument matters, because if the star is closer than the cluster, it shrinks. If it is part of the cluster, it grows. If it is even farther than the cluster, it grows even larger. The same point of light in the sky could be a normal supergiant or the largest star ever discovered, depending entirely on which side of this argument you believe. The star itself, of course, does not care what we think. It just keeps burning. And it has a name problem that confuses almost everyone who tries to study it. 3 names, 1 star, total chaos. If you go online and search for the biggest star in the universe, you will find articles using 3 completely different labels for the exact same object. Some call it Stephenson 2 to 18. Others call it Stephenson 2 DFK1. A third group uses the designation RSGC 201. Even astronomy textbooks sometimes contradict each other, and the average reader ends up convinced these must be 3 different stars. They are the same star. Here is how the mess started. When Charles Stephenson first catalogued the cluster in 1990, he gave the brightest star the simple number 1. Stephenson 2 to 1. Clean, easy, intuitive. The problem is that Stephenson then questioned whether that brightest star even belonged to the cluster. Its location was a little off. Its brightness was suspiciously high. Its motion through space did not quite match the others, so in his original paper, he separated it. He kept it numbered as 1, but flagged it as possibly unrelated to Stephenson 2 itself. Other astronomers picked up the catalogue and disagreed. They argued the star should be included in the cluster proper. They renumbered things. In a 2013 study by a team named Davies, Feiger, and Kudrytsky, the brightest star was given a new label inside their reorganized catalogue. That new label was DFK1, named after the initials of the 3 authors. So now the star had 2 names, Stephenson 2 to 1 and Stephenson 2 DFK1. Then came a third complication. Astronomers studying red supergiant clusters started using a different naming system entirely. They called clusters RSGC, short for Red Supergiant Cluster. Stephenson 2 became RSGC2, and the brightest member became RSGC2-01. If you are keeping score, that is now 3 completely valid catalogue names for 1 star. Things got worse. In 2020, a paper by Roberta Humphreys, one of the most respected astronomers working on supergiants, accidentally referred to this star as RSGC 101. That is the brightest star in a different cluster entirely, located in the same constellation. The mistake propagated. Other papers cited Humphreys' paper. Some of them copied the wrong label. So today, somewhere out there on the internet, you can find articles confidently describing the brightest star in Stephenson 2, using the catalogue name of a completely different star in a different cluster. For most of this video, you will hear the name Stephenson 2 to 18. It is the most widely used label today, and the one that appears in nearly every popular science article. The 18 comes from a renumbering done in a 2007 paper, where the brightest star ended up in position 18 of a reorganized list, rather than position 1. Why does this matter beyond bureaucratic frustration? Because the confusion has real scientific consequences. When researchers go looking for older data on this star, they have to search under 3 different names just to find every paper ever written about it. Some measurements got lost. Some properties got attributed to the wrong object. The full historical record of this star is scattered across catalogues that do not always cross-reference each other. The result is that one of the most famous stars in modern astronomy is also one of the most poorly tracked. Its true history is buried in archives. Its true distance is debated. Its true size depends on which paper you trust and which name they used. A star this big should be impossible to miss. And yet, in a sense, we keep losing it. The only thing every astronomer agrees on is the next number, 2150. Because that number, if it is right, breaks the rules. 2150. That is the number that started the controversy. It refers to solar radii, which is just a fancy way of saying how many of our suns you would have to line up, edge to edge, to span the width of this star. 2150 of them. Take a moment to picture our Sunday. It is already enormous. You could fit roughly 1 million Earths inside it. Its surface, if you could stand on a cooler version of it, would be about 865,000 miles across. Light, the fastest thing in the universe, takes around 2 1/3 seconds just to cross from one side of the sun to the other. Now stretch that span by a factor of 2150. The star we are talking about is roughly 1.5 billion miles across. Light, racing at 186,000 miles per second, takes about 2.5 hours to cross it from edge to edge. A photon born on one side of this star would be older than your morning coffee by the time it reached the other side. The volume calculation is where the brain truly breaks, because volume scales with the cube of radius. So if you stretch a radius by 2000, the volume swells by 8 billion. The actual figure for this star comes out to roughly 10 billion times the volume of our Sunday. 10 billion suns, packed inside one stellar boundary. If you wanted to fill it with planets instead, you would need to flatten and shred more than 7 quadrillion Earths into its interior. That number, written out, has 15 zeros after it, but the size only really hits you when you place it inside our solar system. So that is the next mental exercise. Take this star and gently swap it with our Sunday. Mercury vanishes instantly. Burned, vaporized, gone. Venus, the same. Earth, the same. Mars, the same. The asteroid belt, gone. Jupiter, the largest planet in our system, sits inside the star. The gas giant that has its own miniature solar system of moons would be a small dust mote drifting somewhere inside the lower stellar atmosphere. Saturn, the planet famous for its rings, the planet so beautiful that humans have written poetry about it for centuries, would sit just barely at the edge of the star's outer surface. Some calculations put Saturn slightly inside the photosphere. Others put it just barely outside. The numbers are that tight. This is where the metaphor that gets used over and over comes from. If you replace the sun with this star, its surface would stretch out to where the rings of Saturn currently spin. That is not a clever exaggeration. That is the measurement. And here is the part that nobody emphasizes enough. The star is not solid. There is no hard edge. The surface, what astronomers call the photosphere, is a fuzzy boundary where the gas finally becomes thin enough for light to escape. The whole structure is more like a glowing red mist than a ball. Most of the star is so diffuse that, by Earth standards, it would qualify as a vacuum. The outer layers of this star are thinner than the air in your living room. In fact, parts of it are thinner than the air at the top of Mount Everest. Pieces of it are thinner than the best vacuum chambers on Earth can produce. A star, by mass, mostly empty. A star, by volume, mostly imaginary. But that emptiness is held together by something tighter than steel. Gravity, fighting pressure, locked in a battle the star has been winning for millions of years. The battle, however, has a hard limit. Past a certain size, the math falls apart. Past a certain size, the star cannot hold itself together at all, and this one might already be past that line. Let us walk this out, slowly, because the imagery deserves to land. You are standing on Earth. Today, in your sky, the sun is a yellow-white disk that takes up about half a degree of your view. That is roughly the width of your pinky fingernail held at arm's length. Small, simple, comfortable. Now imagine the sun is gone. In its place, suddenly, sits the star we have been talking about. The first thing that hits you is not heat, it is darkness. Because the surface of this star is cool, astonishingly cool, by stellar standards, where our sun glows at around 10,000 degrees Fahrenheit at its surface, this monster sits at only about 5,400. It glows deep red, the color of dying embers in a fireplace, not the harsh white yellow we are used to. But that gentle color is a trick, because the star is so vast that the total energy pouring out of it is hundreds of thousands of times what our sun produces. The sky would not be brighter than the Sunday. It would be the entire sky. The star would fill your vision from horizon to horizon and then keep going. Its surface, if you replaced our sun with it, would reach about 9.5 times farther out than Earth's current orbit. Earth would not just be inside the star, Earth would be deep inside the star. So would Mars. Jupiter would be roughly a third of the way out toward the surface. Saturn, the ring jewel of our system, would sit almost exactly at the edge of the star, kissing the photosphere. Picture that. The rings of Saturn, spinning quietly at almost 1 billion miles from our current sun, would now be skimming along the upper atmosphere of a red giant. The ice particles in those rings would vaporize within seconds. The planet itself, with its swirling bands and its strange hexagonal storm at the North Pole, would dissolve into a tiny streak of debris being swept up by stellar winds. The orbits we know would be erased. Pluto, way out at the edge of the planetary region, would still be safely outside the star, but it would be orbiting through a region constantly bombarded by hot gas streaming away from the surface, and its frozen nitrogen and methane would boil off into space. The Kuiper Belt, the icy ring of dwarf planets and comet nuclei beyond Neptune, would become a region of melting and evaporating worlds. The Oort cloud, the spherical shell of frozen objects that surrounds our entire solar system, would still survive at its enormous distance, but everything inside it would be transformed. This is the visualization that scientists keep using because, frankly, nothing else gets the scale across. Even seasoned astronomers, people who calculate stellar properties for a living, sometimes pause when they sketch this picture. The numbers are familiar to them. The visualization still surprises them. The brain refuses to fully accept that a single point of light, 18,000 light-years away, could contain everything from Mercury to Saturn inside its boundary. There is something almost unfair about it. We spent generations of human history thinking the sun was the great fire at the center of everything. The Greeks worshipped it, the Egyptians built temples around it. Every civilization on Earth has stories about the Sunday. And then we find this thing, a star so large that our entire sun, plus 8 of the planets in our system, plus their moons, plus the asteroid belt, plus a fair chunk of empty space, would fit comfortably inside it with room to spare. Now, here is the twist. Many physicists believe this picture should be physically impossible. A star cannot get this big, they argue, without tearing itself apart. There is a hard upper limit on the size of a stable red supergiant baked into the mathematics of how stars hold themselves together against gravity. And this monster, if the measurements are right, sits well past that limit. The name of that limit is the next part of the story. And it was discovered, almost casually, by a single Japanese astrophysicist in 1961. His name was Chushiro Hayashi. In 1961, working in Kyoto, Hayashi published a paper that almost nobody outside his small circle of stellar physicists noticed at the time. The paper described a fundamental property of stars, a boundary line drawn in equations, beyond which a stable star simply cannot exist. We now call it the Hayashi limit, and it is the reason scientists keep raising eyebrows at the measurements coming out of Stephenson too. Here is the idea, stripped down to plain language. Every star is locked in a balance. Gravity pulls inward, trying to crush the star into a point. Pressure pushes outward, generated by the heat of nuclear fusion in the core. When these two forces are exactly equal, the star sits stable. Astronomers call this hydrostatic equilibrium, which is a long word for a simple idea. The star is not collapsing, and it is not flying apart. For most of a star's life, this balance is easy to maintain. The core is hot, fusion is steady, and the outward pressure matches the inward pull. But near the end of a massive star's life, things get strange. The core runs out of hydrogen and switches to fusing helium. The outer layers puff up enormously. The star becomes a red supergiant. Its surface cools to deep red. Its volume swells by factors of hundreds or thousands. This is where Hayashi's math kicks in. He showed that, as a star's surface cools below a certain temperature, the way energy flows through the outer layers changes drastically. Instead of light slowly diffusing outward, the outer envelope starts churning. Massive currents of hot gas rise to the surface, dump their heat, and sink back down. This is called convection, and it is the same process that happens in a pot of boiling water, just scaled up to astronomical proportions. Convection is efficient, sometimes too efficient. When a star's surface temperature drops to around 3,500 degrees Kelvin, Hayashi showed that the outer layers become fully convective. The entire envelope, all the way down to deep regions of the star, becomes one giant churning mass. And once that happens, the math says the star cannot get any bigger and stay stable. If you try to make it bigger, you have to make it cooler. And if you make it cooler past a certain point, the equations stop having a solution. The star simply cannot exist in hydrostatic equilibrium beyond that line. On the famous Hertzsprung-Russell diagram, the chart astronomers use to plot every star they study. This limit shows up as a nearly vertical wall. Stars can live to the left of the wall, they cannot live to the right of it. The region beyond is sometimes called the forbidden zone of stellar physics. When you plug realistic numbers into Hayashi's equations, the upper size limit for a red supergiant comes out to roughly 1,500 times the radius of our Sunday. That is the wall. Now look back at our star. 2,150 solar radii. 650 solar radii past the wall. This is the problem. This is the entire problem in one sentence. The most accepted measurement of this star puts it well inside the forbidden zone, where, according to 65 years of stellar physics, no stable star should be able to exist. Either the measurement is wrong, or the physics is incomplete, or this star is doing something we have never seen before. A few possibilities exist. Maybe the distance to the star is wrong, and once we measure it properly, the radius will shrink back below the limit. Maybe the Hayashi equations have an exception nobody has worked out yet, and certain very massive stars can briefly puff out past the boundary before snapping back. Maybe the star is unstable right now, and we are watching it in a brief moment before it tears itself apart. Each of these explanations has its own supporters and its own critics, and each of them has implications that ripple out across the entire study of how stars live and die. To understand why this matters, you need to understand exactly what happens when a star tries to grow past the wall. The answer is not pretty. Imagine inflating a balloon. As you push more air in, the rubber stretches. At first, easy, then harder. Then, suddenly, the surface tension fails, and the balloon either pops or splits. A red supergiant, in some ways, faces the same problem. For a star, the rubber of the balloon is gravity. The air being pumped in is the energy from nuclear fusion deep in the core. As long as gravity can hold the outer layers down, the star stays bound together. As long as fusion keeps producing heat, the star has the pressure to support itself against gravitational collapse. The trouble starts when the star gets too big. As a red supergiant swells, its outer layers move farther and farther from the core. The pull of gravity on those outer layers weakens. The gas at the surface barely feels the star at all. At a radius of around 1,500 suns, the gravitational hold on the outermost gas becomes so feeble that even gentle pulses of energy from the interior can blow material off into space. This is called extreme mass loss, and red supergiants do it constantly. A typical red supergiant sheds gas at a rate millions of times higher than our Sunday. Every year, masses of material equivalent to a sizable planet stream off the star's surface and drift outward into space. The escaping gas forms vast nebulae around the star, glowing dimly in infrared light. These nebulae are essentially the star's own shed skin. Push a star much past 1,500 solar radii, and the mass loss accelerates. The star starts hemorrhaging material. Its outer layers become so loosely bound that they peel away in pulses. Each pulse drives gas outward at enough velocity to escape the star entirely. At that point, the star cannot maintain a stable surface. The outer envelope flickers. The radius shifts up and down by huge fractions over short timescales. Astronomers occasionally catch stars doing this. They are called luminous blue variables, or LBVs, and they are some of the most dangerous and unpredictable stars in the galaxy. They throw off enormous shells of gas every few decades. But there is another reason stars cannot easily exceed the Hayashi limit: convection. When the outer envelope becomes fully convective, the energy transport mechanism changes character. Hot gas rises to the surface, cools, and sinks. The cycle moves heat from the deep interior to the photosphere very efficiently. But this efficiency has a side effect. It cools the outer layers further, which makes the convection even stronger, which cools the outer layers even more. This is a feedback loop. And feedback loops in stellar physics rarely end well. A star trapped in this loop tends to either eject huge amounts of mass and shrink back to a smaller, stable size, or it becomes structurally unstable and enters a chaotic pulsation phase where the surface heaves up and down. Either outcome means the star cannot just sit calmly at a radius of 2,000 suns. It must either be shrinking, pulsing wildly, or already in the process of dying. And here is where the story curls back on itself in a beautiful way. Some astronomers argue that this is exactly what we are seeing with Stephenson 2-18. The star may not be a stable, balanced object at all. It may be a star caught in the act of dying, briefly bloated past every known limit, with its outer layers so loosely held that the entire structure is throwing off material at an extraordinary rate. The star may be days, years, or millennia away from a catastrophic collapse. We are watching its final breath, blown across 18,000 light-years of space, with no way to tell exactly how long the breath has left. Other astronomers argue something simpler. The measurement is wrong, the distance is overestimated, the luminosity is overestimated. Correct those errors, and the star slides back below the Hayashi limit, becoming a more ordinary, if still huge, red supergiant. To choose between these explanations, scientists need to dig into the very heart of what holds a star together. Not just the gravity and the pressure, but the precise balance between them. That balance has a name, and without it, no star, large or small, could exist at all. Every star you have ever seen is engaged in a silent war. The combatants are simple. On one side, gravity, the relentless inward pull that wants to crush everything into a single point. On the other side, pressure, the outward push generated by hot, fast-moving particles bouncing off each other inside the star. The war has no end. It just continues, every second in every layer of every star in the universe. When the two forces match exactly, the star is in hydrostatic equilibrium. The Greek roots of those words mean roughly water standing still. The image is a column of fluid that is not going anywhere because the weight pushing down is perfectly balanced by the pressure pushing up. A star is, in a sense, a giant column of fluid held up by its own internal heat. Picture a single layer of gas, somewhere halfway between the core and the surface. That layer has weight. All the gas above it presses down. All the gas below it presses up. If the upward push is even slightly stronger than the downward push, that layer rises. If the downward push wins, the layer falls. In a stable star, neither happens for very long. The layer just sits there, generation after generation, century after century, in perfect balance. This balance depends on two things continuing to work. First, the core has to keep producing heat. Without fusion energy pouring out from the center, the gas above the core cools. Cool gas exerts less pressure. The balance tilts. Gravity wins. The layers start sinking. Second, the gas has to remain transparent enough for heat to flow outward. If the gas becomes too opaque, heat builds up in pockets and creates instability. If it becomes too transparent, the heat radiates away too quickly and the layers cool. Stars spend almost their entire lives in this delicate balance. Our Sun has been in hydrostatic equilibrium for about 4.5 billion years. It will stay there for another 4 or 5 billion. That is what stable means in stellar terms. Now consider what happens to a star pushing toward the Hayashi limit. In a normal red supergiant, hydrostatic equilibrium still holds, but barely. The outer layers are so far from the core that gravity barely tugs on them. The pressure required to hold them up is small. The balance is fragile, but it holds. Push the star to 2,000 solar radii, and the situation gets dangerous. The outer layers are now so distant that gravity is almost a suggestion. The pressure needed to hold them is tiny, but the pressure being supplied from the hot gas below is fluctuating. Convection currents push waves of energy upward in pulses. Sometimes those pulses push too hard. Sometimes they push too softly. The outer layers heave up and down in response. At this point, the star is not really in true hydrostatic equilibrium. It is in a kind of staggering, oscillating quasi-balance. The radius might shift by a few percent every year. The brightness pulses. The temperature wobbles. The whole structure is straining. Stephenson 2-18, if the measurements are right, sits in exactly this regime. Its outer layers are hanging on by something barely stronger than nothing. Its photosphere is constantly shifting position. Astronomers who track the star's brightness over years see it dimming and brightening in irregular patterns, the visible signature of a structure that cannot quite settle. There is a useful comparison here. Imagine a stack of pillows piled 20 stories high. At the bottom, the pillows are compressed and stable. At the top, each pillow is barely held in place. A gentle breeze could tip the top one off. A stronger gust could collapse the upper third of the stack. The star's outer layers behave the same way. They are pillows balanced precariously on a column of fire. The miracle of stellar physics is that this balance works at all. The miracle of giant red supergiants is that the balance still holds at sizes that should not be possible. When the balance finally fails, the star does not gently fade. It explodes, violently, spectacularly, with enough light to briefly outshine an entire galaxy of 100 billion stars. But before we get to that explosion, there is another piece of the puzzle, because the wall the star is brushing against has a specific shape on the most important diagram in all of stellar physics, and our star sits in a place that wall is supposed to forbid. If you walk into any university astronomy department, somewhere on a wall you will find a chart called the Hertzsprung-Russell diagram. It is named after the two astronomers who came up with it in the early 1900s, and it might be the single most important picture in all of stellar physics. The chart looks deceptively simple. On the horizontal axis, you plot a star's surface temperature. with hotter stars on the left and cooler ones on the right. On the vertical axis, you plot the star's luminosity, with bright stars at the top and dim ones at the bottom. Every star in the sky, no matter how big or small, can be placed somewhere on this chart by knowing just those two numbers. When you do that for thousands of stars, an extraordinary pattern emerges. The stars do not scatter randomly. They cluster into distinct regions. A long diagonal stripe stretches from the upper left to the lower right. This is the main sequence, where stars spend most of their lives quietly fusing hydrogen. Our Sun sits comfortably in the middle of this stripe. Above, and to the right of the main sequence, you find a separate cluster of stars. These are the giants and supergiants, the puffed-up, dying old stars near the end of their lives. Way down at the bottom left sit the white dwarfs, the dense corpses left over after smaller stars die. Every star you have ever seen sits somewhere on this chart, but there is one region of the diagram where almost no stars exist. The far right edge, where stars would be both cool and enormous, is suspiciously empty. There is a nearly vertical line drawn at around 3,500 degrees Kelvin, and almost nothing exists past that line. This is the visualization of the Hayashi limit. Astronomers sometimes call the region to the right of it the forbidden zone. The name is half joke, half serious. The zone is not forbidden by some cosmic decree. It is forbidden by the math of stellar structure. A star sitting in that region cannot maintain hydrostatic equilibrium. It cannot stay together. So, if you plot every confirmed star in our galaxy on the HR diagram, the forbidden zone shows up as a stark, empty space. Almost empty. Because near the very upper right corner, in the region where the most luminous and coolest stars would live, a handful of points show up that should not be there. They are the most extreme red supergiants ever measured. Stars whose published properties place them just barely inside, or right at the edge of, the forbidden zone. Stephenson 2-18 is one of these outliers. When astronomers plot the star using its published temperature of around 3,200 Kelvin and its enormous radius and luminosity, the dot lands in territory that the math says should be uninhabitable. Other stars near the same region include WOG 64 in the Large Magellanic Cloud and NML Cygni in the constellation Cygnus. All of them sit at or past the Hayashi line. What do you do when your data points land in a zone that says no data points should exist? You start questioning the data, and you start questioning the theory, both at the same time. Several explanations have been proposed. One possibility is that the temperature measurements are wrong. Red supergiants are difficult to characterize. Their surfaces are turbulent, dusty, and hidden behind thick stellar atmospheres. A small error in temperature can shift a star across the Hayashi line on the chart. If Stephenson 2-18 is actually slightly warmer than we think, it slides safely back into the allowed region. Another possibility is that these stars are exceptions to the standard theory because of magnetic effects, rotation, or some other process that the simple Hayashi equations leave out. Real stars are complicated. The math behind the Hayashi limit assumes a perfectly spherical, non-rotating, non-magnetic, isolated star. Real stars are messy. They spin. They have magnetic fields. They have binary companions. Any of these could nudge the limit slightly. A third possibility, the most exciting one, is that the theory needs to be updated. Maybe the Hayashi limit is not as firm as we thought. Maybe certain very massive stars can, briefly, push past it. A fourth possibility is that what we are seeing is not really a stable star at all. It is a star in the process of falling apart. Whichever explanation turns out to be correct, the message is clear. The forbidden zone is not as empty as it should be, and the star sitting in it has a story that astronomers have been arguing about for almost 2 decades. The argument begins with one ugly number, a number that, despite all our advances, we still cannot pin down. Almost every wild claim about Stephenson 2-18 traces back to one number, and that number is wrong by possibly more than half. the distance to the star. In astronomy, distance is not just one piece of information. It is the foundation everything else stands on. Once you know how far away a star is, you can convert its apparent brightness into its real brightness. You can convert its angular size into its real size. You can convert its motion across the sky into its real velocity. Get the distance wrong, and every other property becomes wrong by the same factor. For Stephenson 2 to 18, the distance is a mess. When Charles Stephenson first catalogued the cluster in 1990, he estimated a distance of about 30 kiloparsecs, which works out to nearly 100,000 light-years. Later studies, in 2007 and 2010, reduced that to roughly 5.8 kiloparsecs, or 18 to 19,000 light-years. The cluster, in current understanding, sits in the Scutum Centaurus arm of our galaxy, considerably closer than originally thought. But here is the catch. The distance to the cluster is not necessarily the distance to the star. Stephenson 2 to 18's velocity through space, measured by analyzing the Doppler shift of its light, comes out to about 89 kilometers per second. The other stars in Stephenson 2 average about 109 kilometers per second. That is a 20 kilometer per second difference. In astronomical terms, that gap is significant. It is large enough that some researchers argue Stephenson 2 to 18 is not actually part of the cluster at all. It might be a foreground or background star that just happens to lie along the same line of sight. If the star is in the foreground, sitting closer to us than the cluster, then everything shrinks. The radius drops. The luminosity drops. The headlines about the largest known star in the universe quietly evaporate. If the star is behind the cluster, even farther than 19,000 light-years, then everything grows. The radius climbs even higher. The luminosity climbs even higher. The headlines become even more dramatic. If the star is exactly at the cluster's distance, the headlines stay where they are, 2,150 solar radii. Astonishing but unstable, and brushing past the Hayashi limit. So which is it? The frustrating answer is, we do not know. Direct parallax measurements, which are the gold standard for stellar distances, do not work well for stars this far away, buried this deep in galactic dust. The Gaia Space Telescope has revolutionized stellar distance measurements for most of our galactic neighborhood, but heavily reddened stars in dense dust lanes are still tough targets, and Gaia's measurements for Stephenson 2 to 18 carry uncertainties large enough to drive a truck through. One paper has explicitly stated that the relative uncertainty on the distance is greater than 50%. Think about what that means. The distance could be, plausibly, anywhere from roughly 9,000 light-years to nearly 30,000 light-years. That is a factor of 3. Move the star within that range, and its radius could be anywhere from a few hundred to several thousand solar radii. The defenders of the cluster membership argument point out something clever. The 20 km per second velocity difference is actually a typical outflow speed for red supergiants. These stars constantly shed gas in powerful winds. If we are seeing the approaching side of an expanding shell of gas around the star, we might be measuring the velocity of the outflow rather than the velocity of the star itself. In this scenario, the star's true motion through space could match the cluster perfectly, and the strange velocity measurement is just an artifact of looking at outflowing gas. The critics of cluster membership reply that this is a convenient explanation but lacks direct evidence. Until we get cleaner data, the question stays open. So this is where the field sits. The largest known star in the universe is also the star whose properties depend most heavily on a measurement nobody fully trusts. Some scientists treat the 2150 solar radii figure as gospel. Others put quiet asterisks next to it. Still others believe the real number is closer to 1,000 or 1,200, well within the comfortable range of normal red supergiants. The truth is hiding behind dust, distance, and the limits of our instruments. And it might stay hidden for years. But while astronomers argue about how far the star is, one specific piece of evidence keeps coming up. a piece of evidence that points to something different about this object, something that does not quite fit anything else we know. If you want to know whether two stars are gravitationally related, you measure their velocities. Stars in the same cluster were born from the same cloud of gas at roughly the same time. They share a common motion through the galaxy. They drift together, like a flock of birds moving across the sky. The flock might wobble slightly, individual birds might shift, but the average motion of the group is steady and shared. So when astronomers look at a cluster of stars and want to confirm membership, they check the velocities. Stars whose motion matches the average are confirmed members. Stars whose motion is wildly different are flagged as suspicious. For Stephenson 2 to 18, the motion is suspicious. The cluster average comes in at roughly 109 kilometers per second along our line of sight. Stephenson 2 to 18 clocks in at about 89, 20 kilometers per second slower than the rest of the flock. 20 kilometers per second sounds small. In everyday terms, that is over 44,000 miles per hour, which is enormous. But in astronomical terms, where stars routinely move at hundreds of kilometers per second through the galaxy, 20 is noticeable but not enormous. The trouble is what 20 kilometers per second implies. Stars in a tight cluster usually drift together with velocity dispersions of just a few kilometers per second. Larger differences indicate that either the star is not really part of the cluster or something unusual is happening to it. If Stephenson 2 to 18 is genuinely not part of Stephenson 2, then it is a chance alignment, a red supergiant in the foreground or background that happens to sit along the same line of sight when we look up. In that case, its distance is genuinely unknown, and all the published properties are based on an incorrect assumption. If Stephenson 2 to 18 is part of the cluster, something is making it move differently. Several explanations exist. The star could be in a binary system, orbiting an unseen companion that occasionally tugs it forward or backward. The star could be ejecting gas in a powerful asymmetric wind, and the gas we are measuring is moving toward us while the star itself is moving with the cluster. The star could have been gravitationally kicked at some point in its history, perhaps by a close encounter with another star, leaving it with a velocity slightly offset from the cluster average. Each of these scenarios changes how we interpret the star. The asymmetric wind explanation is particularly tempting. Red supergiants are notoriously messy. They puff out gas in irregular pulses, with different parts of the surface losing material at different rates. If we happen to be looking at the side of the star where the wind is blowing toward us, the Doppler shift would make the star appear to be moving toward us faster than it actually is. Astronomers have started looking for evidence of this asymmetry by examining the star's infrared signature. Around Stephenson 2 to 18, there is a faint glowing nebula, the shell of gas the star has shed over the past few thousand years. The shape and structure of that nebula could tell us whether the star is losing mass evenly or in lopsided bursts. Early studies suggest the latter. The dust around Stephenson 2 to 18 appears unevenly distributed. The mass loss looks chaotic, with periods of higher and lower flow rates. This pattern is consistent with a star whose outer layers are unstable, fluctuating, perhaps approaching the end of its life. There is one more piece of evidence worth knowing. The star's radial velocity has been measured multiple times over the years. The numbers have stayed roughly consistent. If the velocity mismatch were due to a binary companion, you would expect the radial velocity to shift back and forth as the star orbited. The fact that it has stayed stable means either the orbital period is very long or there is no companion at all. So the field sits at an impasse. The velocity mismatch is real. The implications are unclear. The star might belong to the cluster. It might not. It might be hiding a companion. It might not. Every published property of Stephenson 2 to 18 carries this uncertainty as a quiet footnote. The astronomers studying it are patient people. They will keep measuring. They will keep refining. Eventually, with better instruments, the question will be settled. But the original mistake about this star's distance, made over 30 years ago, set the entire controversy in motion. And that original mistake is worth understanding, because it shows how a single assumption can ripple across decades of science. Charles Stephenson made a reasonable guess in 1990. It turned out to be wrong by almost a factor of 5. When he first identified the cluster of red stars in his infrared survey, he had no direct way to measure how far away they were. Direct distance measurements, like parallax, were out of reach for objects that deep inside the galactic dust. Stephenson had to estimate. His estimate relied on a clever but flawed technique called spectroscopic parallax. The idea works like this. If you know what type of star you are looking at, you know roughly how bright it should be intrinsically. By comparing that intrinsic brightness to the apparent brightness you see from Earth, you can calculate how far away the star must be to look as dim as it does. The technique is solid when you know the star type accurately. It falls apart when you guess wrong. Stephenson assumed that all the bright red stars in his cluster were classical red supergiants. He used standard absolute magnitudes for that class of star. The calculation produced a distance of around 30 kiloparsecs, roughly 98,000 light-years. If correct, that number would have placed the cluster on the far side of the galactic bulge, well beyond the center of the Milky Way. The cluster would have been one of the most distant objects ever catalogued inside our galaxy. The stars would have had to be among the most luminous red supergiants ever discovered, just to be visible at that range. For 17 years, nobody seriously revisited the calculation. Then, in 2007, a team of astronomers led by Ben Davies took a fresh look. They had access to better instruments and improved understanding of how red supergiants behave. They used a technique called kinematic distance measurement, which estimates distance based on a star's velocity and our model of how the Milky Way rotates. Their answer was dramatically different. The cluster sat at about 5.8 kiloparsecs, roughly 19,000 light-years, about 1/5 of Stephenson's original estimate. The new number changed everything. Suddenly, the stars in Stephenson 2 were not impossibly luminous monsters at the far edge of the galaxy. They were merely very luminous monsters at a more reasonable distance, well inside our own galactic neighborhood. But the brightest star in the group, the one Stephenson had labeled number 1, still stood out. Even at the new closer distance, it was extraordinarily bright, brighter than any other supergiant in the cluster by a wide margin. Its apparent magnitude, combined with the heavy dust between us and it, suggested an intrinsic luminosity of hundreds of thousands of suns. This is when the size estimates exploded. Using the new distance and the star's measured brightness and temperature, researchers calculated a radius of about 2,150 solar radii. The largest known star in the universe was born, scientifically speaking. But notice what happened. The size estimate is built on the distance estimate, which was revised once and could be revised again. If a future paper convincingly argues that the star is actually closer than the cluster, the entire size figure collapses. If a future paper argues the star is farther, the figure grows. The history of Stephenson 2 to 18's measurements reads like a series of revisions. Each revision changed the published properties significantly. Each revision was based on better data than the one before it, but none of them is the final word. The next revision could come any year. This is the part of science that does not always make the headlines. Numbers that look definitive in popular articles are often the result of long, contested measurement chains, each link of which could be questioned. The 2,150 solar radii figure for Stephenson 2 to 18 is a real number based on real data. It is also a fragile number that depends on assumptions that some experts dispute. Future improvements in our ability to measure distance will resolve much of this. There is one specific tool that has already transformed distance measurement across the Milky Way. It launched in 2013 and has been quietly rewriting astronomical catalogues ever since. That tool is named after a Greek goddess of the Earth, and the first time it pointed at a famous supergiant called Scuti, It broke the star's reputation in a single update. The Gaia mission is one of the great quiet revolutions in modern astronomy. Most people have never heard of it. Most people probably never will. But its data has reshaped almost everything we thought we knew about the stars in our galaxy. Gaia is a space telescope, launched by the European Space Agency in December of 2013. Its job is not to take pretty pictures. Its job is to measure positions, motions, and distances of stars with a precision that previous telescopes could only dream of. The mission name was inspired by Greek mythology, but the work it does is purely mathematical. Gaia scans the sky over and over, recording the exact positions of around 2 billion stars. By measuring how each star appears to shift as Earth orbits the Sun, Gaia calculates that star's distance using a geometric technique called parallax. Parallax is the most reliable way to measure stellar distance. Hold a finger up in front of your face and close one eye, then the other. The finger appears to shift against the background. The closer the finger, the bigger the shift. Stars work the same way. From opposite sides of Earth's orbit, 6 months apart, nearby stars shift visibly against the distant background. The amount of shift tells you the distance. Before Gaia, parallax measurements were only reliable for stars within a few hundred light years. Past that range, the shifts became too small to measure accurately. Gaia changed everything. Its instruments can measure shifts so tiny that they can pin down distances out to tens of thousands of light years with reasonable confidence. When Gaia's second data release came out in 2018, astronomers rushed to look up their favorite stars. Many of them were in for a shock. Scutum was one of the casualties. For years, Scutum had been the reigning champion of largest known stars. Its estimated radius was around 1,700 solar radii. Documentaries, textbooks, and YouTube videos featured it prominently. Children who liked space facts could rattle off its size from memory. Then Gaia spoke up. The new parallax measurement showed that Scutum was significantly closer than astronomers had assumed. The revised distance led to a revised brightness, which led to a revised size. The new estimate for Scutum's radius came out to roughly 755 solar radii, less than half of what people had been quoting for decades. Suddenly, Scutum was no longer the biggest. It was not even close. Its new size put it in the same range as Antares, a much more famous red supergiant in the constellation Scorpius. The change rippled outward. Articles had to be rewritten. Lists had to be reordered. The throne of largest known star opened up. Into that opening stepped Stephenson 2-18, with its claimed radius of 2,150 solar radii. It took the crown that Scutum had quietly lost. But the lesson of Scutum hangs over Stephenson 2-18 like a warning. If Gaia could cut Scutum's radius in half with a single revised distance, what might better measurements do to Stephenson 2-18? The current king of stars might be one parallax measurement away from a brutal demotion. The trouble is that Gaia struggles with Stephenson 2-18 specifically. The star sits behind thick clouds of interstellar dust, which dim and redden its light. Its enormous size also creates problems. The photosphere is not a clean point of light. It is a fuzzy, pulsating, extended object whose center is hard to define. Even Gaia's best measurements of this particular star carry uncertainties large enough to leave the question wide open. So we are stuck in a peculiar place. We have the best stellar measurement tool ever built, and it still cannot resolve the controversy around our largest known star. Future Gaia data releases, plus follow-up observations from other instruments, will eventually settle it. The James Webb Space Telescope, with its powerful infrared eyes, has already started looking at heavily dusty stellar regions. Ground-based telescopes with better adaptive optics are coming online. Bit by bit, the fog will lift. For now, we accept the uncertainty. The number we use is 2,150 solar radii, with a quiet asterisk attached. The asterisk reminds us that we might be wrong and that the next paper could change the picture entirely. In the meantime, there is still plenty to say about what is actually happening inside this star right now. Because while we argue about its size, the star itself is doing something extraordinary, something we can see, even from 18,000 light-years away. Its surface is alive. Stand outside on a clear summer day. Watch the surface of a pond. Notice how the water never sits perfectly still. Tiny ripples cross it constantly, driven by the slow rise and fall of temperatures, the breeze, the heat from below. Now scale that pond up by a factor of about 1 billion and replace the water with hot plasma at thousands of degrees, and let the rising columns be wider than the orbit of the Earth. This is the surface of Stephenson 2 to 18. The star is not smooth. Its photosphere, the visible outer layer, is broken into enormous churning cells. Each cell is a convection bubble, a tower of hot gas rising up from deeper in the star, dumping its heat at the top and sinking back down again. The pattern repeats across the entire surface, like an endlessly boiling pot of cosmic soup. On our Sun, convection cells are small. Each one is about 600 miles across. Look at high-resolution images of the Sun, and you can see them as a grainy pattern called solar granulation. Each cell lasts only a few minutes before dissolving and being replaced by another. On a red supergiant, the cells are different. Because the gravity at the surface is so weak and the gas so thin, convection cells in stars like Stephenson 2 to 18 grow to monstrous sizes. Each cell can be 1 or 2 astronomical units across, where 1 astronomical unit is the average distance between Earth and our Sunday. In other words, a single bubble of rising gas on this star can be wider than the entire orbit of Earth. There are probably only a few dozen of these giant cells covering the entire surface at any time. That is a staggering thought. Where the Sun has millions of small granulation cells, this red supergiant has maybe 20 or 30 enormous ones. The surface is not a fine-grained texture. It is a coarse pattern of titanic blobs, each one larger than our entire inner solar system. The cells also live longer. Where solar granules dissolve in minutes, the giant cells on red supergiants persist for months or even years. They rise slowly, they cool slowly, they sink slowly. The whole surface evolves on timescales humans could plausibly observe over the course of a career. This has consequences for how the star looks and behaves. First, the surface brightness is uneven. Some cells, freshly upwelling from deep inside, are hotter and brighter than the surrounding photosphere. Others, where gas is sinking, appear darker and cooler. From far away, the star looks like a glowing red ball with mottled patches of brighter and darker regions slowly shifting position. Second, the star pulsates. As large cells rise and dump heat, they push the upper atmosphere outward slightly. Then the gas falls back. The whole star breathes in a slow, irregular rhythm, expanding and contracting by small fractions of its total radius over months and years. Third, the irregular convection drives mass loss. Bubbles of hot gas push the outermost layers upward, sometimes hard enough to launch material into space entirely. This is part of what makes red supergiants such effective at shedding mass. Their surfaces are essentially throwing gas off in random pulses. Astronomers have actually seen this happening on a similar star, Betelgeuse. In 2019 and 2020, Betelgeuse experienced a famous dimming event. For months, the star got dramatically darker. Wild speculation followed. Some people thought it was about to explode. The eventual explanation involved exactly this kind of convection physics. Betelgeuse had ejected a large cloud of gas from its surface, and as the cloud cooled in space, it condensed into dust. The dust blocked some of the star's light from reaching us. The star did not actually dim significantly. We just lost view of part of its surface behind a temporary curtain. Stephenson 2 to 18 almost certainly does the same thing, only on a larger scale. Its convection cells are bigger, its mass loss is faster, its surface activity is more chaotic. Somewhere out there, right now, an enormous bubble of hot plasma, the size of Earth's orbit, is rising up from inside the star and pushing into the photosphere. By the time we receive the light of that bubble's emergence, 18,000 years will have passed. The light we see today shows the surface of this star as it appeared when humans on Earth were still learning to plant their first crops. By now, the star may look completely different, or it may not exist at all, but its rhythm, the slow heartbeat of rising and falling convection cells, is still beating somewhere in the dust of Scutum, and that heartbeat is what keeps the star alive. The biggest stars in the universe do not sit still, they breathe. Stephenson 2-18, like every red supergiant ever observed, pulses. Its brightness goes up and down over time. Its radius expands and contracts. Its surface heaves outward, then settles back, then heaves out again. The cycle is irregular, the rhythm is messy, but the pulsation never stops. To understand why, you have to picture what is happening inside the outer envelope. Deep inside the star, in the core, fusion is hammering away. Nuclear reactions release a steady stream of energy that flows outward through the layers above. In the inner regions, this energy moves primarily by radiation. Photons bounce around between atoms, slowly working their way outward. In the outer regions, where the gas is cooler and more opaque, energy switches to convection. Hot gas physically carries the heat upward, dumps it at the surface, and falls back. The transition between radiative and convective transport is unstable. Imagine a region where energy is trying to escape, but the gas is too opaque to let radiation through easily. Heat builds up, pressure rises, the gas pushes outward. As it expands, it cools. Cooler gas is more transparent. Suddenly, the trapped energy can escape. The pressure drops, and gravity pulls the outer layers back inward. The gas compresses, becomes opaque again, traps heat again, and the cycle repeats. This is the basic mechanism behind stellar pulsation. Heat traps, pressure builds, expansion happens, heat escapes, contraction happens. A natural feedback loop that turns the entire star into a kind of slow-motion piston engine. On smaller stars like Cepheid variables, this process produces beautifully regular pulsations. The star brightens and dims like clockwork every few days or weeks. Astronomers love Cepheids because their pulsation period correlates directly with their intrinsic brightness. That correlation has been used as a cosmic distance ruler since the early 1900s. Red supergiants are different. Their pulsations are messy. The size of these stars is part of the problem. Convection cells on a red supergiant are so large that they interfere with the regular pulsation cycle. Some cells rise and push the photosphere out at the wrong moment. Others sink and contract the surface unexpectedly. The result is a pulsation that has multiple overlapping frequencies, with no clean period. Stephenson 2-18 has been monitored intermittently for years. Its brightness wobbles up and down by significant fractions over periods ranging from hundreds to thousands of days. Astronomers have not been able to pin down a single dominant period. Several modes seem to be active at once, beating against each other and producing a chaotic light curve. The pulsation has consequences for the star's structure. Each cycle of expansion and contraction stresses the outer layers. Each cycle is a tug of war between gravity and pressure that gravity does not always win cleanly. Over time, the pulsations contribute to the steady mass loss from the surface. Material gets pushed up, sometimes too hard to come back down, and escapes into space. The most dramatic version of this process happens in stars that are pulsating so violently that they reach instability points. At certain combinations of mass, luminosity, and radius, the pulsation becomes self-amplifying. Each cycle pushes harder than the last. Within a relatively short time, the star can lose huge fractions of its outer envelope. There is some evidence that Stephenson 2-18 might be approaching this regime. Its mass loss rate, measured from the infrared glow of dust around it, is much higher than typical red supergiants. The star is shedding material at a rate that suggests its outer layers are barely staying attached. This shedding has produced something visible around the star. A faint, dusty nebula extends outward from Stephenson 2 to 18 for many light years. The nebula is essentially a snapshot of the star's own breath, frozen in space. Material puffed off in the last 10,000 years now hangs around the star in a vast glowing shell. Astronomers can probe the structure of that shell to learn how the star has been behaving recently. What they see is consistent with chaos. The shell is not smooth. It contains denser knots, gaps, asymmetries. The star has been throwing off material in fits and starts, not in a steady wind. A star that breathes that wildly is a star that is uncomfortable. It is a star pushing against its own limits. It is a star whose outer layers are loose enough that any moment of unusual activity could push them past the point of return. The pulsations are not just curious behavior, they are warnings. The star is telling us, in slow flickers of brightness, that something is straining, and the temperature at its surface, which determines the color we see, tells us something else strange. Because as red supergiants go, this one runs cool. Very cool. You would expect a star this bright to be hot. That is the instinct most people have. Hotter equals brighter, right? Light a bigger fire and it burns whiter. Heat a metal rod and it goes from red to orange to yellow to white as the temperature climbs. The same logic should apply to stars. It does not. Stephenson 2 to 18 is one of the most luminous stars in our galaxy, and yet its surface temperature is only about 3,200 degrees Kelvin. By stellar standards, this is freezing. Our Sun has a surface temperature around 5,700 Kelvin. Most main sequence stars run hotter still. Blue supergiants can reach surface temperatures of 30,000 Kelvin or higher. By comparison, 3,200 Kelvin is barely warm. So how can a star this cool be this bright? The answer is size. Total luminosity depends on two things: the temperature of the surface and the total surface area. Hotter surfaces emit more energy per square inch. Larger surfaces emit more total energy because there is more surface to emit from. Even a relatively cool star can dump a staggering amount of energy if its surface area is huge enough. For Stephenson 2 to 18, the surface area is unimaginable. With a radius 2,150 times that of the Sun, the total surface area of this star is over 4.5 million times the surface area of the Sunday. Every cool square inch is dim. There are just so many of them that the total output is overwhelming. The cool temperature also explains the deep red color. Cooler objects glow in longer wavelengths of light, shifting from white-hot toward yellow, orange, red, and eventually infrared. Stephenson 2 to 18 puts out most of its energy in infrared wavelengths that human eyes cannot see. The visible light it produces is heavily skewed toward the red end of the spectrum. If you could somehow stand close to it without being incinerated, the light reaching your eyes would have the color of a deep ember, the kind of dim red glow you see in coals at the bottom of a fire pit. The cool surface has consequences for the chemistry of the star. At 3,200 Kelvin, certain molecules can survive in the upper atmosphere. Most stellar atmospheres are too hot for complex molecules to exist. Atoms move so fast that any chemical bond is shattered within nanoseconds. But on Stephenson 2 to 18, the temperature is low enough that titanium oxide and other simple molecules can form in the outer layers. Astronomers see these molecules in the star's spectrum. Specific wavelengths of light get absorbed by titanium oxide, leaving dark bands in the rainbow of starlight reaching Earth. These bands are a signature of cool, late-type stars. They tell us, without ambiguity, that we are looking at a red supergiant rather than a hotter type of giant star. The cool surface also matters because of where it sits on the Hayashi limit. Recall that the Hayashi limit forms a nearly vertical line on the Hertzsprung-Russell diagram at around 3,500 Kelvin. Stars to the left of that line are allowed. Stars to the right are forbidden. At 3200 Kelvin, Stephenson 2 to 18 sits to the right, inside the forbidden zone. This is the heart of the controversy. Either the temperature measurement is slightly wrong, in which case the star slides back across the Hayashi line, or the temperature is right, in which case the star is doing something the equations say should not happen. Recent work suggests that the most luminous red supergiants might be allowed to dip slightly below the classical Hayashi temperature without immediately falling apart. The standard derivation of the limit assumes a certain set of properties for the stellar atmosphere. Real stars deviate from these idealized assumptions. With modern atmospheric models that include effects like turbulent pressure and convective overshooting, the limit becomes a little fuzzier. But there is a price for letting stars dip into the forbidden zone. They become unstable. Their outer layers heave. They lose mass faster. They cannot stay there for long, in cosmic terms. The cool surface of Stephenson 2 to 18, by this picture, is a sign that the star is approaching the end of its life. The cooling represents the final stages of its expansion as a red supergiant. The star has pushed itself to its maximum size, and the price is a surface that has spread so thin and so far from the heat source that it can barely glow above the temperature of a campfire. That campfire glow is the last warmth before the explosion, because once a red supergiant has cooled this far and expanded this much, it does not have much time left. The clock is ticking, and inside the star, deep beneath the cool red surface, something violent is preparing. How bright is Stephenson 2 to 18? Pick a paper, pick a number, take your chances. If you ask a researcher in 2010, the answer is about 90,000 times the luminosity of our Sunday modest by red supergiant standards. Other stars in the same cluster shine brighter. Stephenson 2 to 18 would be a member of the family but not the star quarterback. If you ask a researcher in 2012, the answer becomes 440,000 solar luminosities. Suddenly, the star is one of the most luminous red supergiants in the galaxy. Articles start using superlatives. Documentary scripts start treating the star as a record breaker. If you ask a researcher in 2020, the answer jumps again. Roberta Humphreys and her team calculated a bolometric luminosity, which measures the total energy output across all wavelengths of around 630,000 solar luminosities. These three numbers refer to the same star. They are not measurement errors in the casual sense. They are honest calculations using different techniques and different assumptions. The first estimate used infrared brightness at specific wavelengths and extrapolated. The second used a more complete spectral analysis. The third built up the total energy budget across the entire spectrum, including the infrared excess from surrounding dust. Each method has merits. Each method has flaws. The factor of 7 difference between the lowest and highest estimates is staggering. In any other field of science, a factor of 7 would mean someone is wrong. In stellar astrophysics, applied to a star 18,000 light-years away, buried behind dust clouds, a factor of 7 is just an honest expression of how hard the measurement is. Why so much spread? Part of the problem is dust. Between Stephenson 2 to 18 and Earth lies a curtain of interstellar gas and dust that absorbs and reddens the star's light. Astronomers have to model how much light is being absorbed before they can calculate how much was originally emitted. Different dust models give different answers. Part of the problem is the star itself. Stephenson 2 to 18 is surrounded by its own personal cloud of shed material. This circumstellar dust glows in infrared when the star's light heats it up. Is that infrared glow part of the star's luminosity or part of the surrounding environment? The answer depends on how you draw the boundary. Part of the problem is the distance, which we have already covered in depth. Take all 3 sources of error, multiply them together, and you get a luminosity that could be off by a factor of several. The published numbers are best guesses based on the best available data at the time. None of them is final. For perspective, Even the most modest estimate of 90,000 solar luminosities is enormous. If our sun were replaced by something that bright, every planet in our solar system would be sterilized within minutes. The light alone, focused on Earth's surface, would vaporize oceans and ignite atmospheres. The highest estimate of 630,000 solar luminosities is in a different category entirely. Stars that bright are rare, even among red supergiants. They sit at the very upper edge of what stellar evolution theories allow. They are usually flagged as candidates for stars in transition, perhaps on their way toward becoming luminous blue variables or other exotic states. The luminosity question matters because brightness, combined with temperature, determines size. If you know how bright a star is and how hot its surface is, you can calculate its radius using a basic physics formula. Make the brightness higher, and the calculated radius grows. Make the brightness lower, and the radius shrinks. This is how Stephenson 2-18's headline size of 2,150 solar radii gets calculated. It assumes the 440,000 solar luminosity figure. If the higher figure is right, the star is even bigger. If the lower figure is right, the star is significantly smaller, perhaps under 1,000 solar radii. The headline number depends on which luminosity you trust. The textbook answer depends on which paper you read. The star itself, of course, has only one true brightness. But that true brightness is hidden behind a fog of competing measurements. Until that fog clears, the star stays a moving target. And there is something else odd about its light, something nobody fully understands. Every star paints a fingerprint in light. When astronomers point a spectroscope at a star, they break its light apart into wavelengths and record how much energy comes out at each one. The resulting plot is called a spectral energy distribution. For a normal star, the curve looks like a smooth hill. It peaks at one wavelength and falls off gradually on either side. The shape of the hill tells you the temperature. For Stephenson 2-18, the hill has a weird shape. When researchers measure the star's spectrum across visible and infrared wavelengths, they find that the energy distribution does not match what a single red supergiant should produce. Some wavelengths show too much energy, others show too little. The curve has bumps and shoulders in places where a clean spectrum would be smooth. This is a problem because spectral curves are supposed to be reliable. They are how we determine the temperature of a star, the type of star, the chemistry of its atmosphere. When the curve is peculiar, every derived property comes with extra uncertainty. What could cause the strangeness? One possibility is that the star has multiple temperature components. Imagine the star's surface is not uniformly at 3,200 Kelvin. Imagine instead that some regions are hotter and some are cooler. Hot convection cells rising from below might briefly heat patches of the photosphere to 4,000 Kelvin or more. Cooler regions where gas is sinking might drop below 3,000 Kelvin. The total light output would be a blend of these different temperatures, producing a curve that does not match any single uniform surface. This explanation has support from theory and from observations of other red supergiants. Betelgeuse, our nearby red supergiant in Orion, shows similar patchiness when imaged at high resolution. Its surface has bright spots and dark spots that change over months. Stephenson 2-18 is too far away to image directly with current technology, but its peculiar spectrum is consistent with similar surface activity on a larger scale. A second possibility is that the spectrum is contaminated by surrounding dust. The shell of material the star has shed glows at certain wavelengths. If we cannot cleanly separate the star's light from the shell's light, the combined spectrum will show features that belong to neither object alone. A third possibility is more exotic. Maybe Stephenson 2-18 is not really a single star. Maybe it is a binary system, with two stars contributing to the spectrum. A red supergiant paired with a slightly hotter companion would produce a blended energy distribution that looks peculiar. There is no direct evidence for a companion, but the possibility cannot be ruled out. A fourth possibility The most worrying one is that the star is structurally unusual. Maybe its envelope is layered in a way that produces atypical light. Maybe its mass loss rate is so extreme that the surface we see is not really the photosphere of a normal star, but a denser layer of outflowing material acting as a kind of optical surface. Stars in this regime, sometimes called pseudo-photospheres, can have weird spectra because we are essentially looking at the wind rather than the star. The spectrum of Stephenson 2 to 18 has been called peculiar enough that it complicates every temperature measurement. Roberta Humphrey's 2020 paper specifically noted that the SED could not be cleanly fitted with standard red supergiant temperatures. The fits the team produced left residuals, places where the model and the data disagreed. This is one of the strongest arguments against treating Stephenson 2 to 18 as a normal red supergiant. Whatever is happening at its surface, it is not the well-understood physics that describes Betelgeuse or Antares or other classic examples of the type. It is something messier. The implications are real. If the spectrum cannot be trusted to give a clean temperature, then the radius derived from that temperature cannot be trusted either. The whole chain of measurements rests on assumptions that the data quietly contradicts. Astronomers tend to use phrases like "further investigation needed" when they encounter this kind of situation. That phrase, in practice, means we do not yet know. What we do know is that the star is losing mass at a rate that suggests something violent is happening just above its visible surface. And the mechanism behind that mass loss has its own dramatic story. A red supergiant does not lose mass by leaking. It loses mass by hemorrhaging. Around Stephenson 2 to 18, gas is streaming outward in a constant, violent wind. Material that has been bound to the star for millions of years is being torn loose and flung into interstellar space. The rate of mass loss is so high that, in a single year, the star sheds an amount of matter equivalent to a small planet. To understand how this happens, picture the outer layers of the star. At the photosphere, the surface temperature is around 3,200 Kelvin. The gas is thin, the gravity is weak. Above the photosphere extends a region called the chromosphere, where the gas becomes even thinner. Above that, the corona, an outer atmosphere of extremely diffuse plasma. Energy flowing from inside the star drives all of these layers outward. In a normal star like our Sun, the outward push is barely enough to launch a small wind. The solar wind carries away materials slowly, and over the entire life of the Sun, only a few thousandths of a solar mass will escape. In a red supergiant, the outward push is enormous. Multiple mechanisms combine to drive the wind. First, radiation pressure. Photons leaving the star push on the gas they encounter. In a star this luminous, the total push from light alone is significant. The pressure of radiation is enough to lift the lightest layers off the surface and accelerate them outward. Second, dust formation. As gas rises away from the surface and cools, certain elements condense into solid grains. Silicates, carbon, iron compounds form tiny dust particles in the upper atmosphere. These grains absorb starlight far more efficiently than gas alone. They feel an enormous radiative push and accelerate rapidly outward. As they go, they drag the surrounding gas with them through collisions. This is the most important driver of mass loss in cool red supergiants. Third, pulsations. The breathing rhythm of the star pushes outer layers upward in pulses. Each pulse adds momentum to the wind. Some pulses are strong enough to launch material at velocities above the escape speed, sending it off into space permanently. For Stephenson 2 to 18, all three mechanisms are operating at maximum. The luminosity is enormous, so radiation pressure is high. The temperature is cool enough that dust forms readily in the upper atmosphere. The pulsations are vigorous and irregular, providing the extra kick to launch material. The combined wind has been measured by analyzing the dust shell around the star. the mass loss rate comes out to a value far higher than typical red supergiants. Some estimates suggest the star is losing mass at rates similar to the most extreme red supergiants ever observed, perhaps comparable to VY Canis Majoris. This rate cannot be sustained indefinitely. At current loss rates, the star would shed its entire outer envelope within tens of thousands of years. That sounds like a long time in human terms, but it is a heartbeat in stellar evolution. Stephenson 2-18 is essentially in the final act of its life, peeling away its outer layers in real time. The wind has visible consequences. The shed material does not vanish. It piles up in space around the star, forming a vast nebula of dust and gas. This nebula glows in infrared light as the star's energy reheats the dust. From Earth, even with no direct image of the star itself, we can detect the infrared signature of this expanding shell. The shell tells a story. By measuring its thickness, density, and chemistry, astronomers can reconstruct the recent history of the star's mass loss. The story they read is one of episodic, asymmetric, increasing outflow. The wind has not been steady. It has come in surges, with periods of higher and lower mass loss. The pattern is consistent with a star whose outer envelope is becoming progressively more unstable. The star is, in a slow-motion sense, evaporating. And as it evaporates, it produces something that astronomers can use to learn even more about its surface. Something brighter, in certain wavelengths, than the star itself. In the dense, dusty regions just above the surface of Stephenson 2-18, something is amplifying microwave light. The phenomenon is called a stellar maser. The name is an acronym for microwave amplification by stimulated emission of radiation. It is essentially a natural laser, except instead of producing visible light, it produces light in the microwave portion of the spectrum. The same kind of light your microwave oven uses to heat food. How do you build a natural maser? You need the right conditions, a large volume of gas, a specific kind of molecule, a way to pump energy into the molecules so that they all reach an excited state at once, and then a passing wave of microwave light to trigger them, causing them to release their stored energy in a coherent burst. Around red supergiants, these conditions occur naturally. In the cool, dense regions a few stellar radii above the photosphere, water molecules, hydroxyl molecules, and silicon monoxide molecules form readily. The star's intense infrared radiation pumps these molecules into excited energy states. When a passing photon of the right wavelength interacts with one of them, it triggers the molecule to release its energy at the same wavelength, in phase with the incoming photon. The result is an amplified beam of microwave light. The brightest maser emissions from red supergiants come from water molecules. The water maser line sits at 22 GHz, a wavelength of about 1 centimeter. Observatories around the world have been tracking water masers from cool giants for decades. The maser light is bright enough to be detected even from very distant red supergiants like Stephenson 2-18. For our star, the maser emission is exceptional. When astronomers surveyed the red supergiants in Stephenson 2 for maser activity, they found that Stephenson 2-18 had some of the strongest maser emissions in the entire cluster. The brightness of the masers correlates with the density of gas around the star and the rate of mass loss. Strong masers mean a lot of material is flowing outward from the surface. The maser line also gives astronomers a high-precision way to measure motion. By tracking the Doppler shift of the maser emission, researchers can determine the velocity of the gas producing it. This is part of how we know the gas around Stephenson 2-18 is moving differently from the other stars in the cluster. The maser observations have produced one particularly interesting result. The shape of the maser emission suggests that the gas around the star is not symmetric. Different parts of the maser show different velocities, with some pointing toward Earth and others pointing away. This pattern is consistent with a non-spherical outflow, gas streaming outward in a lopsided pattern rather than a clean, expanding shell. Why does the outflow look lopsided? Several possibilities exist. The star might be rotating fast enough to flatten the wind into a disc-like pattern. The star might have a binary companion whose gravity is sculpting the gas. Magnetic fields might be channeling material in specific directions. Or the convection cells at the surface might simply be ejecting material more energetically in some regions than others. Whatever the cause, the maser results add another piece of evidence that Stephenson 2-18 is doing something unusual. The cleaner, more symmetric maser patterns seen around other red supergiants like Betelgeuse and Antares look different from what we see here. The masers of Stephenson 2-18 are louder, messier, and more asymmetric. If you could somehow tune a radio receiver to 22 GHz and point it at the constellation Scutum, you would pick up these masers as a steady hum coming from a single point in the dust. The hum would be the sound of water molecules, vaporized off a dying red giant, screaming in microwave light as they drift outward through space. This is some of the strangest information we receive from the star. A radio signal made by molecules of water generated by physics that humans only learned to harness in laboratories in the 1950s. Nature has been running this experiment for billions of years, and the molecules doing the singing are part of an even larger structure, a shroud of dust that hides the star's true face. When you look at Stephenson 2, 18 inches visible light, you do not really see the star. You see a faint, reddened smudge that even powerful telescopes struggle to resolve. Most of what the star produces is hidden. Two things are hiding it. The first is the dust that lies between us and the star, scattered through tens of thousands of light years of interstellar space. The second is the dust around the star itself, the material it has been shedding for the last several thousand years. The interstellar dust is unavoidable. Anywhere you look through the plane of our galaxy, you are looking through clouds of microscopic dust grains. These grains scatter and absorb starlight, especially at shorter wavelengths. Blue light gets blocked more than red light, which is why distant stars in the galactic plane look redder than they really are. Stephenson 2-18, viewed through 18,000 light-years of this material, is dimmed and reddened significantly. The circumstellar dust is more interesting. It is the personal cloud of material the star has built up around itself over the centuries. Here is how it forms. Gas streams off the star's surface in the powerful wind we have been describing. As the gas cools while moving outward, certain elements reach temperatures at which they can no longer remain in gaseous form. Silicon, magnesium, iron, carbon, and other heavy elements condense into solid particles. These particles are tiny, ranging from a few atoms across to grains the size of fine smoke. They form a cloud that extends outward from the star to distances of light years. The dust cloud is not visible in ordinary light. It is too cold and too diffuse to produce its own visible emission. But it absorbs the star's radiation and re-emits the energy as infrared light. This infrared glow is how astronomers detect and study the cloud. Around Stephenson 2-18, the cloud is enormous. Infrared observations show a shell of glowing material, extending several light years from the star. The shell contains a mass of dust that, by some estimates, totals more than the mass of the Sunday. All of it was once part of the star's outer envelope. The shell is not smooth. High-resolution infrared imaging reveals clumps, gaps, and asymmetries. Some regions are denser, suggesting moments when the star ejected unusually large bursts of material. Other regions are sparser, indicating quieter periods. The dust cloud is essentially a fossil record of the star's recent past, etched in infrared photons. By studying the chemistry of the dust, astronomers can learn what elements the star has been producing in its interior. Stephenson 2-18, like all red supergiants, has been fusing helium and heavier elements in its core. Some of those heavier elements get dredged up to the surface and ejected with the wind. The dust shell contains traces of carbon, oxygen, silicon, and other products of late-stage stellar fusion. The shell has another important function. It feeds back into the star's environment. Once the dust drifts far enough away to cool below the temperature where solar wind ablation matters, it becomes part of the interstellar medium. The material returns to the galactic ecosystem, where it can eventually be incorporated into new stars and planets. This is one of the great recycling processes in the galaxy. Massive stars like Stephenson 2-18 are essentially factories that take simple elements left over from the Big Bang, fuse them into heavier ones in their cores, and then return the products to space through stellar winds and eventual supernova explosions. Without this process, the galaxy would have no carbon, no silicon, no iron. Planets like Earth would not exist. Living organisms made of those same elements would not exist. In a strange sense, the dusty shroud around Stephenson 2-18 is part of the next generation of cosmic chemistry. The dust that obscures our view of the star is, by mass, almost certainly the raw material of some star or planet that has not yet been born. But the recycling is not complete yet. The biggest contribution Stephenson 2-18 will make to the galaxy is still ahead of it. And what is happening inside the star right now is the engine that will eventually drive that contribution. Far below the cool red surface, the heart of Stephenson 2-18 is a furnace running on the heaviest elements it can manage. To understand what is happening inside, you need to know how stellar fusion progresses through a massive star's life. In its youth, a star like Stephenson 2-18 burned hydrogen. In its core, where temperatures reached around 15 million Kelvin, hydrogen nuclei fused together to form helium. This is the simplest and longest stage of fusion. It powers our sun and almost every other star on the main sequence. For Stephenson 2-18, the hydrogen burning stage lasted only a few million years. Massive stars burn through their hydrogen quickly because their cores are hotter and the reactions run faster. When the hydrogen ran out, the core contracted. Gravitational compression heated the gas to over 100 million Kelvin. At that temperature, helium nuclei could fuse together to form carbon in a process called the triple alpha reaction. 3 helium nuclei collide, 2 of them stick briefly, and a third joins to form carbon. The process is rare and inefficient, but it produces enormous energy because of how massive the star is. Helium burning lasted only a few 100,000 years for Stephenson 2-18. During this stage, the outer envelope swelled up enormously. The star became a red supergiant. We do not know exactly which fusion stage Stephenson 2-18 is in right now. Several pieces of evidence are consistent with helium core burning, but other interpretations are possible. If the star is currently fusing helium in its core, it has roughly a few 100,000 years left before that fuel runs out. After helium, the next stage would be carbon burning, which would last only a few 100 to a few 1,000 years. Each successive stage runs for a shorter and shorter time because the reactions produce less energy and the star burns through fuel faster. After carbon burning comes neon burning, then oxygen burning, then silicon burning. The silicon stage is the last. It lasts only days, maybe a week or 2 at most. At that point, the core consists primarily of iron, and iron cannot fuse to release energy. Fusion stops. Gravity wins instantly. The star collapses. The collapse triggers a supernova. This is the fate of every star above about 8 solar masses, including Stephenson 2-18. But here is where the uncertainty creeps in. Stephenson 2-18's mass is poorly known. The published estimates range from about 20 to 40 solar masses, but the actual value could be lower if the radius and luminosity have been overestimated. Different masses lead to different fates. If the star is on the lower end of the mass range, it will end its life as a classical Type II supernova. The iron core will collapse to form a neutron star, and the outer layers will be blown off in an enormous explosion visible across the galaxy. If the star is on the higher end, it might collapse all the way to a black hole. In some scenarios, this collapse fails to produce a visible supernova at all. The star simply vanishes from view as its mass disappears beyond the event horizon of the new black hole. A few such failed supernovae have been observed in other galaxies in recent years. If the star is somewhere in between, the supernova might be unusual. Stars with extremely massive envelopes and high mass loss rates can produce strange explosions, including pair instability supernovae, hypernovae, and other exotic events. We will not know which fate awaits Stephenson 2 to 18 until it happens. And it might already have happened. 18,000 years is plenty of time for a star this far along in its life to have died. The light reaching us today shows the star as it was during the last ice age. Anything could have happened since then. This is the eerie reality of looking at distant stars. We see them in the past. The present version of Stephenson 2 to 18 might be a glowing supernova remnant, or a quietly collapsed black hole, or it might still be patiently fusing helium. The light reaching us today will not tell us for thousands of years. But if the star is still alive in the present, its core is racing toward the moment when it cannot sustain itself any longer. The countdown has a specific endpoint, and the endpoint has a name. Every massive star is born with a death sentence. The sentence is written in iron. Iron is the heaviest element that can be produced by fusion while still releasing energy. Anything lighter than iron, when fused with another nucleus, gives off a tiny amount of energy in the process. Hydrogen fusion releases energy. Helium fusion releases energy. Carbon, neon, oxygen, silicon, all of them release energy when they fuse into heavier elements. Iron is different. Iron sits at the bottom of the nuclear binding energy curve. To fuse iron into anything heavier, you have to put energy in rather than take energy out. The reaction does not work spontaneously. Fusion in a stellar core stops cold when it reaches iron. This is what dooms massive stars. For most of its life, a star supports itself against gravity using the outward pressure from fusion energy. As long as the core is producing energy, the gas in the layers above is hot and dense and pushy. It holds up the weight of the star. When iron forms at the core, the energy production stops. Gravity does not stop. The outer layers continue to press down, but there is no energy coming up to support them. The collapse is immediate. Picture a tower held up by an internal fire. The fire goes out. The tower falls. Stellar collapse is faster and more violent than any other process in nature. The iron core, which is roughly the size of the Earth, collapses in less than a second. Pressures and temperatures reach levels that exist nowhere else in the universe. The atoms of iron get crushed so hard that their electrons are forced into their nuclei, combining with protons to form neutrons. Within moments, what used to be a ball of iron the size of Earth becomes a ball of pure neutrons the size of a city. The collapse releases an enormous amount of gravitational energy. Most of this energy escapes as neutrinos, ghostly particles that pass through matter almost unaffected. A tiny fraction of the energy, less than 1%, gets deposited back into the surrounding layers of the star. That tiny fraction is still vast. It is enough to drive a shockwave outward through the entire star. The shockwave accelerates the outer envelope to thousands of kilometers per second. The outer layers blow off into space. The visible explosion can be seen across millions of light years. This is a Type 2 supernova. It is one of the most violent events in the universe. For Stephenson 2 to 18, the countdown to this event might be very short. The star is in the late stages of its life. Even by red supergiant standards, it is showing signs of advanced age. The extreme mass loss, the chaotic pulsations, the cool, puffy envelope all point to a star nearing the end. If the star is in helium core burning, it has perhaps a few 100,000 years left. If it has already moved on to carbon burning, that number drops to a few thousand. If it is in silicon burning, the explosion could come in our lifetime, or it could have already happened. We have no way to know which stage the star is currently in. The interior is hidden from us by the cool envelope. Only the supernova itself, when it finally arrives, will tell us how close we were. There is something humbling about this. 18,000 light years away, a star that has been quietly preparing for catastrophe for the last several thousand years, sits at the end of a chain of events that began before the first humans walked the Earth. The chain will end with a flash of light bright enough to outshine an entire galaxy. We might see that flash any night, or we might wait 100,000 years. The universe does not telegraph its biggest events ahead of time. When the flash comes, it will be one of the most informative astronomical observations of our species' history. We will learn exactly what was happening inside this star. We will resolve all the controversies about its size, its mass, its structure. The supernova will be a forensic report on every property we have argued about, and it will be visible from Earth without a telescope. The supernova of Stephenson, 2 to 18, will be a spectacle that humans, if they are still around to see it, will never forget. Type 2 supernovae are the explosions of massive stars whose cores have collapsed. They unfold in a specific sequence of stages, and each stage is dramatic in its own way. In the first few seconds, the iron core collapses to form a proto-neutron star. The infalling material rebounds off the dense neutron core and produces a shockwave. The shockwave initially stalls in the dense layers just above the core. It would die out completely if not for one of the strangest mechanisms in stellar physics: neutrinos. The collapse releases 10 to the 53 joules of energy in the form of neutrinos, a torrent so vast that the total energy output rivals the entire visible output of every other star in the universe combined for a few seconds. Most of the neutrinos escape immediately because they barely interact with matter, but a small fraction, perhaps 1%, get absorbed by the gas behind the stalled shockwave. This deposition reheats the gas. The shockwave restarts. It begins moving outward again. Over the next hours, the shockwave plows through the layers of the star. It accelerates the outer envelope to thousands of kilometers per second. It compresses and heats material, triggering nuclear reactions that produce heavy elements like nickel, cobalt, and traces of even heavier metals. When the shockwave reaches the surface, the star brightens dramatically. The light curve climbs rapidly over a few days, peaking at a brightness millions to billions of times that of the Sunday. For Stephenson 2 to 18, the peak brightness could outshine an entire dwarf galaxy. For weeks afterward, the supernova fades only slowly. The energy now comes from the radioactive decay of nickel-56 produced in the explosion. Nickel decays to cobalt, then to iron, releasing gamma rays that heat the expanding debris and keep it glowing. The light curve of a Type 2 supernova has a characteristic shape, with an initial peak followed by a long plateau lasting weeks or months. From Earth, 18,000 light-years away, what would we see? The supernova would appear as a new bright star in the constellation Scutum. At maximum brightness, it would likely be visible to the naked eye even during daylight. It would shine brighter than any planet, brighter than the full moon at times, perhaps even rivaling the brightness of the daytime sky over short periods. Over the following weeks, the supernova would fade, dropping into the range of bright stars in the night sky. It would remain visible without a telescope for many months, possibly more than a year. It would become the most studied object in modern astronomy, with every telescope on Earth and in space pointed at it continuously. The scientific harvest would be enormous. Neutrino detectors deep underground would pick up the first signal hours before the visible light reached us. The neutrinos travel through the star almost instantly, while the light has to fight its way through the outer layers. The neutrino burst would give us a few hours warning. Then the light would arrive. Spectrographs would record the explosion's chemistry in detail. Polarimeters would measure the asymmetry of the explosion. Radio telescopes would track the expanding shockwave as it slowed and interacted with surrounding material. Decades later, the supernova remnant would still be glowing in radio waves and X-rays, a slowly expanding bubble of debris from one of the most massive stars our galaxy contains. For the people watching, the experience would be transformative. A new bright star, appearing suddenly and lasting for months, has historically been treated as a sign by every civilization that has witnessed one. The supernovae that humans have actually seen with the naked eye, like the famous one in 1054 that produced the Crab Nebula, are still talked about in cultures around the world 1,000 years later. The supernova of Stephenson 2 to 18 would be even more visible than the famous historical ones, because the star is more massive and likely to produce a brighter explosion. It would be remembered as long as humans remember anything, but the visible flash is only the beginning. What gets left behind after the explosion is just as strange as the star that produced it. When the dust settles, something will remain at the center of where Stephenson 2 to 18 used to be. The question is what? Type 2 supernovae leave behind one of two possible remnants. The iron core that collapsed inward, depending on its mass, either stabilizes as a neutron star or continues collapsing to form a black hole. The split happens at a specific mass threshold. Quantum mechanics tells us that neutrons exert a pressure against being squeezed together too tightly. This is called neutron degeneracy pressure. It is enough to support the collapsed core against further collapse, as long as the total mass of the core stays below a certain limit. This limit is called the Tolman-Oppenheimer-Volkoff limit, and it sits at roughly 2 to 3 solar masses. If the leftover core mass is below this limit, it stabilizes as a neutron star, a ball of pure neutrons about 12 miles across, with a density so high that a teaspoon of its material would weigh as much as a mountain. Neutron stars often spin rapidly, throwing off beams of radio waves from their magnetic poles. When those beams sweep past Earth, we detect them as pulsars. If the leftover core mass exceeds the limit, neutron degeneracy pressure cannot hold it up. The collapse continues. The core falls inside its own event horizon, becoming a black hole. The visible universe loses access to the matter forever. For Stephenson 2 to 18, the prediction depends entirely on the original mass of the star and on how much mass it loses before the supernova. Stars with initial masses below about 25 solar masses tend to produce neutron stars. Stars above about 25 solar masses tend to produce black holes. The boundary is fuzzy and depends on metal content, rotation, and other factors. Stephenson 2 to 18's mass estimates fall in or near the transition region. Older estimates put the star at around 40 solar masses. Newer estimates suggest it might be lower, perhaps in the 20 to 30 range. The amount of mass the star has already lost to its wind is uncertain. The amount it will lose between now and the supernova is also uncertain. If Stephenson 2 to 18 is on the lower end of the mass range, it will produce a neutron star. The supernova will be a classical Type 2 event, leaving behind a rapidly spinning magnetized core that we might eventually detect as a pulsar in the Scutum constellation. If it is on the higher end, it will produce a black hole. The supernova might still be visible, perhaps even brighter than a typical Type 2 event, or, in some scenarios, it might be unusually dim. Some massive stars collapse to form black holes without a bright explosion at all. The outer envelope falls inward along with the core, and the star simply disappears. These quiet collapses, sometimes called failed supernovae, are a relatively new discovery. Astronomers have caught a few of them in other galaxies, where a star visible in one image is simply gone in the next, with no bright explosion in between. The mechanism is not fully understood, but it appears that some massive stars are massive enough that even the neutrino-driven shockwave cannot blow off the outer layers. For Stephenson 2 to 18, this scenario is a real possibility. The star is in the mass range where failed supernovae are most likely. We could observe a relatively faint flash, or nothing visible at all, while a stellar mass black hole quietly forms in the center of Scutum. If a black hole does form, it would weigh somewhere between 10 and 20 solar masses. It would be one of the largest stellar mass black holes in our region of the galaxy. It would not be visible directly, but its gravitational presence could affect any nearby stars or gas clouds. A black hole of this size sitting 18,000 light-years away is no threat to Earth. The mass is too small and the distance too large to cause any gravitational disturbance. But it would be a fascinating object to study. Black holes formed by failed supernovae are particularly interesting because they preserve more of the original star's properties than black holes formed in violent explosions. Either way, Stephenson 2-18 will end its life as a compact object, a point of intense gravity in the middle of an expanding cloud of debris. The star that broke the laws of physics during its life will become an object that bends those same laws in death, and the explosion that creates it will be visible from Earth. The question is what that view actually looks like. Picture the night sky on a future date that nobody has marked on a calendar. You step outside to look at the stars. Something is wrong. There is a new point of light in the southern sky, in a part of the heavens that should be relatively empty. It is brighter than any star you have ever seen. It is brighter than Venus, brighter than Jupiter. It is, in fact, the brightest object in the sky after the sun and moon. This is the supernova of Stephenson 2-18, finally reaching Earth. The light that struck your eyes left the star 18,000 years ago. During those 18,000 years, your ancestors learned agriculture, built civilizations, invented writing, developed mathematics, walked on the moon, and built telescopes to study the very star whose dying light is now flooding into your retinas. The first phase of the supernova would be a rapid brightening over a few days. The exact peak brightness depends on the type of explosion. A bright Type 2 supernova at 18,000 light-years could reach an apparent visual magnitude of around -8 or -9. That is bright enough to be visible during the day, brighter than any natural object except the sun and moon. It would cast shadows at night. For the first week or two, the supernova would be impossible to ignore. People would point at it from every continent. Telescopes would be redirected away from their previous targets. Every major astronomical institution would shift its entire research program to focus on the new explosion. The brightness would slowly drop over the following weeks. After about a month, the supernova would still be one of the brightest stars in the sky, comparable to Sirius or Canopus. After several months, it would fade to the brightness of an ordinary bright star. After a year, it would still be visible to the naked eye on dark nights. After several years, it would require a telescope to see it all. Throughout this entire period, the chemistry and physics of the explosion would be studied in unprecedented detail. The closest supernova in modern times occurred in 1987 in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. That event, called Supernova 1987A, was studied with all the instruments available at the time, and it became one of the most informative astronomical observations ever made. A supernova at Stephenson 2-18's distance would be much closer and brighter than Supernova 1987A. The amount of data we could collect would be staggering. Astronomers could measure the spectrum at high resolution for years, watching the chemistry of the expanding debris evolve. Neutrino detectors would record the precise neutrino signature, comparing it to theoretical predictions. Polarimeters would measure the geometry of the explosion in detail. The cultural impact would also be enormous. Historical records show that previous naked-eye supernovae left lasting marks on the civilizations that witnessed them. The supernova of 1054 was recorded by Chinese astronomers and showed up in Native American rock art. The supernova of 1572 was studied by Tycho Brahe and helped overturn the medieval belief that the heavens were unchanging. A future supernova of Stephenson 2-18 would be one of the great events of the century in which it happened. Photographs and videos of the new bright star would circulate everywhere. Religious and philosophical discussions would draw on the event. Even people with no interest in science would learn the name of this star. How long until this happens? Honestly, we do not know. The star might have already exploded thousands of years ago, and we are just waiting for the light to arrive. The star might explode tomorrow, or in a century, or in 100,000 years. Red supergiants are not predictable. They give few warning signs that the end is imminent. Astronomers occasionally joke that the best birthday gift you could give an astronomer is a nearby supernova. Stephenson 2-18 might deliver one of the best ever recorded, but the explosion will also affect more than just Earth. The shockwave will travel outward into the surrounding region of the galaxy, and what it does there is its own story. A supernova does not just produce light, it produces a physical shockwave of material, expanding outward at thousands of kilometers per second. That shockwave eventually slams into anything in its path. When Stephenson 2-18 explodes, the immediate region around it will be transformed. In the first few years after the explosion, the outer envelope of the star, blown off in the supernova, will expand into space at velocities approaching 1% of the speed of light. The ejected material will form a roughly spherical shell of hot gas, rich in heavy elements forged in the explosion and the late stages of the star's life. For nearby stars, this shell is bad news. If any star is within a few light-years of Stephenson 2-18, the shockwave will reach it within centuries. The hot, dense material will compress the target star's atmosphere, strip away its outer layers, and dump enormous amounts of radioactive material into the surrounding space. Any planets orbiting that star would have their atmospheres torn off and their surfaces sterilized by intense radiation. Out to about 30 light-years, the supernova's hard radiation alone, especially the burst of gamma rays and X-rays in the first weeks, can damage planetary atmospheres. Ozone layers can be destroyed. The surface of any unprotected planet would be flooded with cosmic rays and ultraviolet light for years. Beyond 30 light-years, the direct effects become much smaller. The shell of debris continues expanding, but slows as it sweeps up interstellar material. After a few thousand years, the shockwave is moving at only a few hundred kilometers per second, and it stops being dangerous to individual star systems. The good news is that there are no known planetary systems within 30 light-years of Stephenson 2-18. The bad news is that we do not really know the local environment of the star in detail. The dust and distance make it hard to map. There could be cool, dim stars and planets out there that we have not detected. For Earth, 18,000 light-years away, the supernova poses no direct danger. The hard radiation will be diluted by distance to harmless levels. The shockwave will eventually reach us, but only after about 100,000 years. And by then, it will be moving slowly and have dispersed widely. By the time it gets here, it will just be more interstellar gas, indistinguishable from the rest of the galactic medium. The dangerous distance for a supernova affecting life on Earth is generally estimated at around 50 to 100 light-years. Within that range, the explosion can do real damage to our atmosphere and biosphere. There is no star within that distance that is close to going supernova. Betelgeuse, the nearest red supergiant to Earth, is roughly 640 light-years away, far enough to be perfectly safe. Even if it explodes tomorrow, Stephenson 2-18, at 18,000 light-years, is so far that its supernova would be a spectacular show with no danger attached. The light would be the only thing reaching us in any meaningful way. But the explosion would have one important consequence for our galaxy. It would seed the surrounding region of space with heavy elements. The carbon, oxygen, silicon, iron, and other metals produced inside the star over its entire life would be flung out into the interstellar medium. There, they would mix with the gas already present and eventually become part of new stars and planets forming in the same region. This is how the universe builds up complexity. Each generation of massive stars produces heavier elements, dyes, and seeds the next generation. Without this process, the universe would still be mostly hydrogen and helium, with no carbon, no oxygen, no iron, no rocky planets, no life. Stephenson 2-18, when it dies, will have a meaningful impact on the chemical evolution of our region of the Milky Way. Future stars forming in the same area will be slightly richer in heavy elements than they would have been without this explosion. Future planets will have slightly more rock-forming materials available. Future life forms, if they emerge in such planets, will have a slightly richer chemical palette to work with. The biggest known star, in death, will be a chemical donor to everything that comes after it. But it is not the only contender for the title. Several other monsters lurk in the cosmic catalogue, and any of them could overtake it. Stephenson 2 to 18 is not alone in the upper reaches of stellar size. A handful of other stars, scattered across our galaxy, and a few nearby galaxies, occupy the same extreme region of stellar parameters. Each of them is enormous. Each of them is poorly understood. Each of them has been at one point or another a candidate for the title of largest known star. The most famous historical contender is VY Canis Majoris. Located in the constellation Canis Major, about 3,900 light-years from Earth, this red hypergiant has been studied extensively since the 1800s. Its current size estimate is around 1,420 solar radii. Big, but smaller than Stephenson 2 to 18, VY Canis Majoris held the title of largest known star for many years before being overtaken. Then there is WO G64 in the Large Magellanic Cloud. This is a satellite galaxy of the Milky Way, about 160,000 light-years from Earth. WO G64 has an estimated radius between 1,500 and 1,730 solar radii. It is one of the largest stars in the Magellanic Clouds and a strong candidate for one of the largest red supergiants overall. Recent observations have produced one of the most detailed images of a distant red supergiant ever taken, showing its enormous dust cocoon and its asymmetric surface. NML Cygni, in the constellation Cygnus, is another strong contender. Its radius estimates range from about 1,000 to roughly 1,500 solar radii. The star sits inside a dense star-forming region called the Cygnus OB2 Association, surrounded by a complex environment of gas and dust. Like Stephenson 2 to 18, its properties are difficult to pin down because of the surrounding material. UY Scuti was once the reigning champion, but has since been demoted. After Gaia parallax measurements were applied, its radius dropped to about 755 solar radii. Still impressive, but no longer in the running for the largest star title. Westerland 1 to 26 is a red supergiant in the massive young cluster, Westerland 1, located about 10,000 light-years away. Its radius is estimated at around 1,500 to 2,000 solar radii. Strong measurements have placed it at the upper edge of what current theory allows. Mous Fa, the famous Herschel's garnet star, is a red supergiant about 3,000 light-years away. Its radius sits in the range of 970 to 1,260 solar radii. It is one of the brightest red supergiants visible to the naked eye from Earth. All of these stars have one thing in common. Their properties are uncertain enough that any one of them could plausibly be the largest, depending on which measurements you trust. The race for largest known star is not really a race at all. It is a moving target, shifting every time new data comes in. Different methods of measurement, different assumptions about distance, different models of stellar atmospheres, all produce slightly different sizes. The ranking changes from paper to paper. Stephenson 2 to 18 currently holds the headline number, but the science community has not unanimously crowned it the champion. If you ask different astronomers which star they consider the largest, you will get different answers. Some will say Stephenson 2 to 18, some will say WO G64, some will say one of the others. A few will tell you that the question itself is not well posed, because stars this size do not have clean boundaries, and the comparison is meaningless past a certain point. The honest answer is that we have a cluster of red supergiants at the upper end of stellar sizes, all of them flirting with or exceeding the theoretical limit, all of them in the late stages of their lives, all of them destined to explode at some point in the next few 100,000 years. Stephenson 2 to 18 is special, not because it is provably the biggest, but because its claimed size is the most extreme. Of all the candidates, it is the one whose published radius most clearly violates the Hayashi limit. It is the most dramatic outlier on the chart. Whether or not it turns out to be the true champion, it is the most useful test case for asking how far stellar physics can be pushed. But there is another property of these monster stars that is even more counterintuitive than their size. something that almost nobody who hears about them for the first time can immediately accept: how light they are. A star 2,150 times wider than the Sun should be heavy. It is not. This is one of the strangest facts about red supergiants. Their masses, while still enormous in absolute terms, are tiny compared to what their sizes would suggest. Stephenson 2 to 18's mass estimates range from about 20 to 40 solar masses, with significant uncertainty on the exact value. Consider the math. The Sun has a mass of about 2 times 10 to the 30 kilograms. Stephenson 2 to 18 has roughly 20 to 40 times that mass. So we are talking about a star that masses maybe 4 to 8 times 10 to the 31 kilograms. But the volume is 10 billion times the Sun's volume. So the average density of Stephenson 2 to 18 is about 3 to 7 billion times less than the average density of the Sunday. The Sun's average density is roughly the same as water, around 1 gram per cubic centimeter. Divide that by a few billion. The resulting density is in the range of a billionth of a gram per cubic centimeter. In other words, the average density of Stephenson 2 to 18 is less than the density of air in your living room, less than the density of air at the top of Mount Everest, less than the density of the upper atmosphere of Earth. Most of Stephenson 2 to 18 is, by Earth standards, vacuum. How is this possible? Where did all the mass go? The answer lies in the structure of red supergiants. The mass of these stars is concentrated in the core. The core is small and incredibly dense, perhaps the size of Earth, but with a mass equal to most of the star itself. Above the core, the layers grow progressively thinner and less dense as they extend outward. By the time you reach the photosphere of Stephenson 2 to 18, the gas density is incredibly low. The visible surface of the star is essentially a dim glow from a region of plasma so thin that you could probably walk through it without immediately noticing, except for the temperature, which would still vaporize you instantly. The mass distribution inside the star is dramatic. If you imagine slicing the star into concentric shells, almost all the mass sits in the innermost few percent of the radius. The outer 90-something% of the radius contains a tiny fraction of the mass. The star is mostly stretched out atmosphere, with a small dense furnace at the middle. This structure is what makes the Hayashi limit relevant. The outer layers are held against gravity only because the inner regions still produce enough heat to support them. As the star ages and the heat output fluctuates, the outer layers can puff up enormously, even without much additional mass being added. The mass paradox has implications for how we should think about red supergiants. These are not solid balls of matter. They are not even gas balls in the simple sense. They are stretched, thin, fragile structures held together by a delicate balance of forces that could fail at any time. A red supergiant is more like a hot air balloon than a planet. Most of the volume is hot, thin gas. A small core does most of the work of generating buoyancy. The whole structure depends on continued heating to stay aloft. If the heating fails, the balloon collapses. If the heating fluctuates, the balloon wobbles. If the balloon gets too big, it tears at the edges. This image, more than any size comparison, captures what these stars actually are: enormous fragile envelopes around small, dense engines, hanging on by physics that gets weaker as the star grows. And the densities, when you look at them in detail, are even stranger than the bulk averages suggest, because the surface of Stephenson 2 to 18 is so diffuse that it would barely register as gas. If you could scoop a teaspoon of gas from the surface of Stephenson 2 to 18 and bring it back to Earth, you would find almost nothing in it. The surface gas of red supergiants is so thin that it qualifies as a near vacuum by Earth standards. The density at the photosphere is roughly 1 billion times less than the density of air at sea level. By some measurements, it can be even lower in the outer atmosphere, dropping to levels comparable to laboratory vacuums. This is so strange that it bears repeating. The visible surface of a red supergiant, the layer that emits the light we see, is thinner than the air at the top of the highest mountains on Earth. thinner than the air in the stratosphere, thinner than some of the better vacuum chambers humans can build in laboratories. Yet that thin layer glows with the energy of hundreds of thousands of suns. The trick is volume. Even though each individual cubic centimeter of the photosphere contains very few atoms, the photosphere itself extends across an enormous surface area. Stephenson 2-18 has a surface area roughly 4.5 million times the surface area of our Sunday. Even sparse gas, spread across that much area, can emit huge amounts of light. The thinness of the outer layers explains several of the star's behaviors. It explains why mass loss is so easy. The atoms at the surface are barely held in place. A small push from radiation, dust, or pulsations is enough to launch them into space. It explains why convection cells are so large. In dense gas, convection has to overcome significant resistance from neighboring layers. In thin gas, large bubbles can rise unimpeded over enormous distances. It explains why the temperature is so low, thin gas radiates inefficiently. To radiate the same amount of total energy, it needs either much higher volume or much lower temperature. Stephenson 2-18 chose the volume route. Its surface temperature dropped as it expanded, settling at the cool, deep red end of the stellar temperature range. It explains why the surface is unstable. A solid object can hold its shape against perturbations. A diffuse cloud of gas cannot. Every fluctuation in pressure, every burst of radiation, every passing convection cell can disturb the surface and change its position. It explains why the star pulses. The thin gas has a natural oscillation frequency that depends on the size and structure of the star. Small disturbances can excite this oscillation, and once excited, it persists for centuries. The thinness even explains, in a sense, why the size estimates are so uncertain. A star with a sharp, solid boundary would have an unambiguous size. A star whose surface is a diffuse cloud blends gradually into space. The photosphere is defined as the layer where the gas becomes opaque enough to absorb most of the light passing through it. But this is a definition based on optical depth, not on a physical edge. Different definitions and different observation wavelengths give slightly different sizes. The closer you look at Stephenson 2-18, the harder it is to draw a clean line and say this is where the star ends. There is the dense core. There is the gradually thinning envelope. There is the wind launching from the upper atmosphere. There is the dust shell extending light years into space. Where does the star itself stop and its environment begin? The answer depends on what you are measuring. The photosphere is one boundary. The outer atmosphere is another. The edge of the wind acceleration region is another. The outer edge of the dust shell is yet another. For a star this large, the question "what is its size?" is less straightforward than it sounds. 2,150 solar radii refers to one specific definition of the boundary. Other definitions could give larger or smaller numbers. This is the deeper truth that the simple headline number conceals. Stephenson 2-18 is not really a ball with a known size. It is a complex, layered, dynamic system whose physical extent depends on how you measure it. The argument over whether it violates the Hayashi limit is, in part, an argument over how to draw the boundary at all. The lesson for stellar physics is that the limits we draw are themselves only approximations. Real stars are messier than the equations predict, and our messy biggest known star has something to teach us about the very process that creates stars in the first place. If Stephenson 2-18's measurements are correct, our theories of how massive stars work are incomplete. That is the deepest implication of this single star. Not that we got one measurement wrong, not that we need slightly better tools. The implication is that our framework for understanding massive stellar evolution has gaps that this star reveals. Several specific lessons emerge. The first concerns the upper limit of stellar size. For decades, the Hayashi limit at around 1,500 solar radii has been treated as a firm wall. Stephenson 2-18, if real at 2,150 solar radii, says the wall is permeable, at least temporarily. Some massive stars can briefly exceed the wall, perhaps during late stages of evolution when their atmospheres become extremely loose and unstable. The wall is not absolute. It is a guideline. This, in turn, has implications for stellar evolution models. The codes that simulate how massive stars age over millions of years incorporate the Hayashi limit as a constraint. If real stars sometimes exceed the limit, the models need to be updated to handle this regime. The updates are not trivial. Stars that exceed the limit are doing something unusual, and capturing that physics requires careful additions to the simulations. The second lesson concerns mass loss. The rates at which red supergiants shed material into space directly affect what kind of supernova they eventually produce, and what kind of remnant they leave behind. If extreme red supergiants like Stephenson 2 to 18 are losing mass at rates higher than older models predicted, then the final masses and structures of these stars need to be recalculated. The connection between initial stellar mass and final outcome may need adjustment. The third lesson concerns the diversity of supernovae. As we discover that some red supergiants can become extreme outliers in size and mass loss, the variety of possible supernovae expands. Some explosions might be brighter than expected, some might be dimmer, some might fail entirely. The neat categories we use to classify supernovae are probably oversimplifications, and stars like Stephenson 2 to 18 sit at the boundaries where the categories blur. The fourth lesson is about measurement uncertainty. The whole story of this star is a lesson in how hard astronomy can be. Even with modern instruments, even with space telescopes and decades of follow-up observations, we cannot pin down a single star's basic properties to better than a factor of 2. The universe is messy. The data is noisy. The interpretations are model-dependent. Anyone who claims to know exactly what a distant star is doing should be regarded with caution. The fifth lesson is philosophical. Limits in physics are not always absolute prohibitions. Sometimes they are statistical generalizations, places where the average behavior of matter falls off rapidly. Stars are rare past the Hayashi limit, but rare is not impossible. The universe is large enough to contain rare exceptions to its own rules. Stephenson 2 to 18 might be one of those exceptions, briefly puffed up past the standard limit before it dies. This last lesson applies broadly. Many of the limits we teach as fundamental boundaries in physics are really just typical limits, with rare exceptions hiding in the extremes. The discovery of Stephenson 2 to 18 invites us to look for other such exceptions elsewhere in the universe, other physical regimes, where stars, or planets, or galaxies might be doing things that standard theory says are forbidden. Astronomers are increasingly finding such cases. There are galaxies that should not exist as early in the universe as we observe them. There are planets in orbits that should not be stable. There are black holes, too massive for their host galaxies. The universe keeps presenting us with outliers that force us to refine our theories. Stephenson 2 to 18 is part of this pattern. A star that, taken at face value, breaks the rules. A challenge to the textbooks. A reminder that the cosmos is more inventive than our equations. The honest scientific response is humility. We do not know everything. The next paper, the next observation, the next instrument may reveal something we never anticipated. The frontier of astrophysics keeps moving outward, and stars like this one are signposts pointing toward the unknown. And the deepest possibility is that this signpost is pointing somewhere we have not yet looked. There is one possibility that no astronomer wants to say out loud, but that hangs over every conversation about Stephenson 2 to 18. What if everything we think we know about this star is wrong? Not in the small sense of a measurement being off by 20%. In the large sense of our entire understanding of the object being mistaken. The star might not be a red supergiant at all. Some researchers have suggested that the peculiar spectrum, the extreme mass loss, the unusual velocity, could indicate that Stephenson 2 to 18 is something else entirely. A red supergiant in transition to a luminous blue variable, a binary system whose interactions confuse our interpretations. An object in the middle of a phase change that lasts only a few thousand years and produces properties unlike any normal stellar category. The star might not be where we think it is. The 50% distance uncertainty is large enough that the true distance could place the star in a completely different part of the galaxy than the cluster it appears near. If it is much closer than the cluster, it is a smaller, normal red supergiant. If it is much farther, it is a different kind of object entirely. The star might not be what we think it is. Some observations have hinted that the photosphere we see might not be the true surface of the star at all, but a dense layer of outflowing material that mimics a stellar surface. Stars in this regime, sometimes called optically thick winds, can produce light curves and spectra that look like normal supergiants, but with very different underlying physics. The star might not even be a single star. Binary or multiple systems with one massive component can produce all kinds of strange observational signatures. A binary companion hidden inside the dust shell could explain the unusual velocity, the peculiar spectrum, and the chaotic light curve. Each of these possibilities has been raised in the scientific literature. None of them has been ruled out. None of them has been confirmed. The star sits in a regime where multiple competing interpretations remain viable, and the data we currently have cannot definitively choose among them. This is not a failure. This is how astronomy works. We make our best guess based on available evidence. We publish papers. Other researchers question our guesses. New data comes in. The picture sharpens or shifts. The process is slow. It can take decades to settle questions about a single distant star. For Stephenson 2 to 18, the process is ongoing. Future observations with the James Webb Space Telescope, the extremely large telescope under construction in Chile, and the next generations of radio interferometers may finally produce data clean enough to resolve the controversies. Or those observations may produce new puzzles we have not anticipated. The history of astronomy is full of cases where better instruments revealed not the expected refinements, but entirely new questions. What is certain is that the star will keep its secrets a while longer. And what is also certain is that, somewhere in the constellation Scutum, 18,000 light-years away, a vast red glow continues to burn and pulse and shed its outer layers. The light reaching Earth right now left the star 18,000 years ago. By the time it reached our atmosphere, civilizations had risen and fallen. Languages had been born and forgotten. Continents had shifted. Ice ages had ended. And an entire species had spread across the Earth and built telescopes powerful enough to capture that ancient light. When we measure 2,150 solar radii, we might be measuring a star that no longer exists. The supernova may have happened thousands of years ago, and the wave of light from that explosion may be racing toward us right now, somewhere along its 18,000-year journey. We might step outside tomorrow night and see a flash where the star used to be, or we might wait 1,000 generations. The universe does not announce its biggest moments. It just sends the light when it sends the light, and we catch what we can. Whatever Stephenson 2 to 18 turns out to be, it has already given us something valuable, a reason to look harder, a reason to question our limits, a reason to keep building better instruments and asking better questions. A star that might break the rules of physics, a star that might already be dead, a star whose true nature might not be settled in our lifetime. And somewhere out there, hidden in dust and distance, the star burns on, indifferent to our arguments, burning the only fuel it has left, waiting for the moment when even gravity can no longer hold it together. When that moment arrives, every question we asked about it will be answered at once, in a single flash.